start. Good morning, everyone. Welcome to the third day of the Graph Algorithms workshop. It is my pleasure to introduce the first speaker of the day, Professor Sanjeev Khanna. Professor Khanna is the Henry Salvatori Professor of Computer and Information Science at the University of Pennsylvania. He earned his PhD from Stanford University in 1996 under the advice of Rajiv Motwani, following which he spent 3 years at Bell Laboratories before joining UPenn. Professor Khanna has made several key contributions in theory CS and has been named an ACM Fellow in 2018 for his contributions to approximation algorithms, hardness of approximation, and sublinear algorithms. He has also been the recipient of the prestigious Guggenheim Fellowship and the Sloan Fellowship. So join me in welcoming Professor Khanna. Over to you, Professor.
Thank you. Thank you. I'm thrilled to be part of this exciting workshop, and thanks to the organizers for including me in the program. So in my talk today, I want to share with you a set of ideas and connections that I have personally found fascinating, and I hope you will too. These ideas have led to conditional dream result for the fully dynamic matching problem. But at the same time, they highlight several really exciting questions to work on, and hopefully some of you will get interested in working on these questions. Okay, so just a quick recap of the matching problem. Matching in a graph is a set of vertex disjoint edges, and the maximum matching problem is to find the largest such set. So in the toy example here, the red edges form a matching, and they also happen to form a maximum matching. Now the focus of this talk is going to be the fully dynamic matching problem, where instead of working with a static graph, we are interested in maintaining a near optimal size matching in a graph that's being continually updated by edge insertion and deletion updates. Okay? This is a problem that Thachapol talked about also on first day in this wonderful two-part tutorial. So what's the goal? The goal is to design an algorithm that is able to maintain a near optimal matching with a small update time. Specific goal that we would be interested in would be to maintain a 1 minus epsilon approximate matching, where think of epsilon as an arbitrarily small constant which is tending to 0. So we want to come as close to optimality as possible, and we want to understand what's the update time needed to achieve this goal of maintaining a very close to optimal match. Okay. Throughout the talk, I'm going to use the convention that n will be always number of vertices and m will denote number of edges. Okay, so what do we know about fully dynamic matching? It has a long and rich history. Hopefully, this small list already convinces you of that, and in particular you can see just last 10 to 15 years have seen a lot of activity on this problem. I'm just going to highlight a few relevant trade-offs so that you have some context for the problem we are working on. So first, if we are interested in maintaining a half approximate matching, and in particular a maximal matching, which is always a half approximation, we have really a fantastic result here. You can maintain it essentially in constant update. Okay? Now, if we demand something better, so the next interesting landmark is 2/3 approximation. Now we are getting closer and closer to optimality, but there is a jump in the update time. The best known update time is square root n for this goal. And then for the 1 minus epsilon approximation, which is the problem that we are interested in this talk, the best known update time was order root m over epsilon square. This is a result due to Gupta and Penn from 2013. And m can be as large as n squared, so this is really essentially an order n update time result. Okay? And so this is where, things stood for about next 10 years or so. And you can see how the jumps are happening in the update time as we demand better and better approximation quality. And so the question that has been an outstanding question here is that is it possible to get a 1 minus epsilon approximate matching in update time, which is strictly better than n?
So these are worst case update times, not the amortized one there.
These are worst case update times, but we didn't know anything for amortized either. Okay, so then about a few years ago, we were able to get a small improvement over the n update time. And in particular, we were able to achieve 1 minus small o of 1 approximation with an update time n over polylog star n. Okay? So it's just a moral improvement over the n barrier, but it kind of showed that n is not the right answer for this goal. And then a few months later, Yang Liu got a bit more substantial improvement, which is n over 2 to the root log n time. But note that neither of these are going below n by a polynomial factor, okay, which is kind of what we really wanted to achieve. So here is a picture summarizing the state of the art. On the x-axis, I have the approximation ratio. On the y-axis are the update times. And you can kind of see how the jumps are happening as we go from 1/2 to 1 minus small o of 1. Okay? Just as an aside, let me mention, I went from half to 2/3. A few years ago, Sohail and I found some other interesting trade-offs that can be achieved between 1/2 and 2/3. That's the dotted line with BK22. But that's not of interest for this talk, so I won't say anything more about that. Okay, so the motivating question for this talk is there a fully dynamic algorithm for every constant epsilon greater than 0 to maintain a 1 minus epsilon approximate matching, which has an update time which is strictly better than n to the 1 minus omega 1. Okay? So n to the 0.99 would be a great result. And the rest of this talk I'm going to assume without loss of generality that the size of the maximum matching is omega n. There is a standard vertex sparsification trick which allows you to make this assumption without loss of generality. Okay? So along the way, if I come up with a scheme which has an additive error of small o of n, then you know it's a 1 minus small o of 1 approximation. Okay, so here is a very natural approach for working towards this goal. Instead of working directly with the input graph G, which may have n square edges, let's work with the sparse subgraph H of G, which is sparser, but at the same time captures most of the optimal matching. It approximately preserves matching. Okay. Now, if you have such a subgraph H, you could run the Gupta-Pang algorithm on this subgraph. And the Gupta-Pang algorithm gives you an update time of roughly square root m. If m is n to the 2 minus omega 1, we got our result. Right? Okay? So to make this approach more precise, let me introduce formally what's the concept of a sparsifier for matching. You are familiar with such a concept for cuts, and it has been discussed on day 1 and 2, cut sparsifiers. So for matching, the concept that we are going to use is the following. An alpha matching sparsifier of a graph G is a subgraph H which has the following property. Give me any two disjoint sets A and B of vertices. Then the size of the largest matching between A and B in the sparsifier H is within alpha and error of the size in the original graph G. So you're preserving matchings to within additive error of alpha. Okay. You might wonder, why do I allow additive error? Why not multiplicative like we do for cut sparsifiers? It's easy to see. If I wanted multiplicative approximation, the only sparsifier of any graph is the graph itself. Okay? Because if I look at any edge uv and give it to you as my set A and B, you have to know whether the edge uv exists or not. Right? Okay.
Demystify why is somewhat stronger requirement for any two subsets.
Okay, good. So the reason is that the graph is evolving. Yes, we care about only the matching in the entire graph, but since the graph is evolving, by making insertions and deletions of edges, I could turn your attention to now, to get a large matching, find me a large matching among this set AB. Okay? Rest of it is taken care of. Here is where you have to now solve the problem. Okay? Good. Okay, so this is exactly the plan that we actually executed in this n over polylog star n update time result a few years ago. So in particular, we showed that there is a order n square time algorithm which creates a 1 over polylog star n matching sparsifier that contains n square over polylog star n edges. Okay. And so this sparsifier is preserving matchings to within an additive error of n over polylog star n, and if the opt is omega n, this is small o of 1 multiplicative error. And the idea for getting this result is just relying on Zemiridis regularity lemma. An algorithmic version of this lemma is what we need to get this result. Okay, so just to recap how this is used, we are going to periodically recompute this matching sparsifier, and it can be shown that the sparsifier is robust. It can withstand a very long sequence of edge updates and still remain a valid sparsifier. Then we run the Gupta-Peng algorithm on the sparsifier, but m has now become n square over polylog star n. So square root m is n over polylog star n. This is as simple as that. Okay, so can we push all this further? Why stop at n over polylog star n? Maybe there is better sparsifiers, right? So in order to understand full power of this very simple natural approach, we need to understand two things. What is the optimal size of a small o of 1 matching sparsifier? That is, the error will be additive small o of n. And the time needed to compute such a matching sparsifier, even if the optimal size is small, if time needed to compute it is large, it will defeat the purpose for our application, because we will have to pay for that time in our fully dynamic algorithm. Okay, let's start with the first question, which is the necessary condition to get anything out of this approach. So can we get much smaller than what we created as a small o of 1 matching sparsifier? Turns out the answer to this question is very closely connected to a famous problem in math, namely understanding density of Ruzza-Zemiridi graphs, okay, or RS graphs. Okay. So let me explain what these graphs are. They're going to play a central role in the rest of this talk. So in order to define these RS graphs, we need to first understand the notion of an induced matching in a graph. So what's an induced matching in a graph? It's a matching with the property that you have no other edges present but the matching edges present between the vertices participating in the matching. So if you look at this picture, those red edges, they form an induced matching. If you look at those 6 vertices, those red edges are the only edges there in the graph. There are no other edges. So what's an RS graph? It's a graph whose edges can be partitioned into large edge disjoint induced matching. Okay? What is large? Anytime I say large, you should think omega n size. Okay? So really large induced matching. Okay? So here is an example of an RS graph which has 4 induced matchings of size 3. Here is the first matching, second, every time you can verify it's an induced matching, third, and fourth. Good. So each induced matching is of size omega n. Locally, the definition of RS graphs is actually enforcing a very strong sparsity condition. I gave you these omega n size vertices participating in this omega n size induced matching. I require all those omega n square remaining edge slots cannot have an. So it would seem like such graphs cannot be very dense, right? Maybe order n log n edges, no more. Right? Turns out they can indeed be extremely dense. So let me use the following parameterization, which I will use throughout the talk. Rs of n comma beta n denotes the largest number of induced matchings that you can pack in an n vertex Rs graph when each matching has size beta n. Okay, and beta is a constant between 0 and 1, 4. Okay, so what do we know? We know that this number is sandwiched somewhere between n to the 1 over log log n and n over 2 to the log star n. Okay. So n to the 1 over log log n is not polynomial, but it's very close to being a polynomial. Okay. So in terms of the number of edges, this is saying the number of edges in such a graph ranges between n to the 1 plus 1 over log log n. We can construct such a graph with omega n size induced matching, and at most n square over 2 to the log star n edges. Narrowing this gap is a major open problem. Okay, and it will have these graphs have huge number of applications. So any progress here will have implications on number of other things. Okay, so what's the connection between these graphs and our sparsifier problem? Here is one direction of a connection, which is very easy to show. Size of the alpha matching sparsifiers of a graph G is lower bounded by size of the RS graph, which consists of induced matching of size roughly alpha n. So if those graphs are dense, you can't hope for small alpha matching sparsifier. Okay? Why? The proof is just one line. Okay, so let me show it to you. Let's take an RS graph which has induced matchings of size alpha plus delta n. Delta is some vanishingly small constant. Okay? Now build an alpha sparsifier of this graph. Take an induced matching of size alpha plus delta times n. You must keep at least delta n edges from this matching in your sparsifier. Otherwise, your error on this set will be more than alpha n. Moreover, these matchings are induced, so edges you keep for one matching can never help you for any other matching. So in every matching, you're keeping a constant fraction of the edges. So the size of the sparsifier has to be roughly same as the size of such a graph. Okay? Turns out there is a converse connection too. This is it. These graphs completely essentially characterize the size of an alpha matching sparsifier. You can show that any graph G has an alpha matching sparsifier whose size is roughly n times Rs of n comma alpha n over 8. Okay? So it's not exactly alpha n, but it's just off by a constant. Okay? And 8 can be optimized further, but the clean proof just leads to 8 here. Okay? So what does this tell us? It tells us if you're looking at figuring out the size of these alpha matching sparsifier, then that quantity is sandwiched somewhere between n to the 1 plus small o of 1 and n to the 2 minus small o of 1. This gives hope for conditional results. Suppose that quantity s of n comma alpha, which is the size of an alpha matching sparsifier, is close to n to the 1 plus small o of 1. Then if we feed such a sparsifier into Gupta-Pang algorithm, it will give us n to the half plus small o of 1 after time. So that seems at least a promising avenue for conditional results. Right? There is a problem. We don't know how to efficiently construct such matching sparsifiers. The proof of this theorem is via an exponential size LP. And we don't know anything more efficient, any more efficient way of getting to this result, but solving that exponential size LP. Okay. So that's a problem.
But this is a harder problem. In the sense that you're saying like, so these RS graphs are the worst case, but in your fully dynamic algorithm, somehow the insertion and deletions has to maintain this RS property for quite.
And actually, you can create sequences where this RS graph property will emerge.
Persist.
Yes, you can actually create such sequences. Yes. So it's not just a theoretical worry. Yeah. Okay, so that problem turns out is not a real hard barrier. There is a way around that problem if we introduce a small twist in the definition of RS graph. A very small twist, but it will turn out to be very powerful. So what's the twist? It's this new notion called ordered RS graphs. And what are these graphs? So this time, the matchings are going to be presented to you as an ordered sequence. So these induced matchings that we were looking at, before they were just a collection, now they're going to be an ordered sequence, M1, M2 to M70. Each matching has large size, beta n. But now, the matching Mi is required to be induced only with respect to the prefix of the first I matching, okay? Not the entire collection. So here is an example of a graph that's not an RS graph, but an ORS graph. Okay? Why is this not an RS graph here? Because the matching M1 is not induced. There is an M2 edge straddling. But it's an ORS graph. M1 is induced with respect to the edges in M1, no problem. And M2 is actually induced with respect to M1 union M2. That you can see that M2 is an induced matching. Okay. So every RS graph is an ORS graph, but the converse is not true as shown here. Okay, but it seems like a very small twist, right? Because if you think about halfway down, all the matchings you're encountering, they are induced with respect to another half of the matching. So it seems like a small twist, right? And of course, you know, since every RS graph is an ORS graph, you can basically inherit those bounds. You know, they're sandwiched in essentially the same range. Okay, so what does this twist buy us? There is a beautiful result of Sohail Benezad and Alma Ghaffari, which shows the following. With this twist in place, you can come up with 1 minus epsilon approximate matching, a fully dynamic algorithm for maintaining a 1 minus epsilon approximate matching, where the update time is going to be square root n times square root of ORS of n comma theta n. So remember, ORS of n comma theta n is sandwiched between n to the small o of 1 and roughly n. So if that quantity turns out to be optimistically n to the small o of 1, we are basically getting n to the half plus small o of 1 update time, which was the dream result, you know, as suggested by the previous discussion. Right? And so you would actually are achieving that if the ORS density turns out to be n to the small o of 1. And at this point, it may seem like this is it. That's the ultimate limit of this approach, right? But a few months later, we were able to push it actually much further, and we were able to get a result which shows an update time of n to the small o of 1 times ORS of n comma theta n. So which means if the ORS of n comma theta n turns out to be n to the small o of 1, you have a fully dynamic matching algorithm with an update time of n to the small o of 1. It's a conditional result, right? Hoping for something good to happen on the density front. But if it comes to pass, then our goal of beating n is kind of realized in a very strong sense. We would reach n to the small o of 1 update time. Okay. So in the remaining time, I want to show you the beautiful ideas that are behind the BG24 algorithm, and then I will also explain to you how, just very briefly at least, how the plan for getting our improvement. Okay?
Sanjeev,
Yeah.
before you move on, so just to make sure I understand, so ORS being like n to the smaller one is saying that all RS graphs are sparse, like there are no
All
dense.
ORS graphs are, yes, sparse, right. sparse meaning n to the 1 plus mod of 1. Yes, yes. Yes, it's the number of matchings you pack, yes. So. Okay, so now we'll just focus on the BG24 algorithm and then how to push things further from there. Okay. So the key problem that we are going to work with for understanding these ideas is what I'll refer to as the induced subgraph matching problem, or ISM. So what is this problem? I give you a graph G and I give you a subset U of vertices in this graph. And I promise to you the induced subgraph on U contains an omega n size matching. Your goal is to find a constant factor approximation to this matching. Okay. I don't care how bad that constant is. It could be 1,000 approximation, but that's all I want you to do. Okay. Now, what's the relevance to our goal of 1 minus epsilon approximation? Well, it can be shown that computing a 1 minus epsilon approximate matching in a graph can be reduced to solving f of epsilon adaptively chosen instances of ISM. So epsilon will be some very small constant, but it will be a constant for us. So really, 1 minus epsilon approximate matching is same as solving order 1 instances of ISM. Okay? So from here on, we are just going to think about, we are interested in solving ISM instances because that's really going to be same as getting the 1 minus approximate matching.
In the ISM instance, you are also specified U as a.
You're given U. Yes, yes. I will give you U. U will be adaptively changing. You're basically building augmenting paths, you can think, okay, by solving these things. Okay? So you can think of these kind of theorems as boosting results. They take a weak approximation algorithm and turn it to something much stronger. Okay? Good. Okay, so what is this telling us? Well, suppose we had an algorithm that could solve ISM in n to the 2 minus delta time. Right? Then we will actually get a fully dynamic matching algorithm which has an update time of n to the 1 minus delta. Why? You start with the 1 minus epsilon approximate matching. It's going to remain a good quality matching for next theta n updates. After that, I'm going to recompute a new 1 minus epsilon approximate matching. And how do I recompute? I'll solve some f of epsilon, order 1 instances of ISM. Okay. So the cost of solving ISM instances, constant number of them, times n to the 2 minus delta, can be amortized over theta n updates, giving me an update time of n to the 1 minus delta. Okay. Okay. So by now, what might start to feel like a predictable pattern, I raise your hopes about a possible algorithmic strategy, but then I also give you the bad news. The bad news here is that there is no algorithm for ISM that can beat n squared time. Okay? You need omega n squared time to solve ISM. So why is that? Here is kind of an example that shows you why this is the case. So imagine in this graph, U is the set L2 union R2, and between this set of vertices there lies an induced matching, a perfect induced matching. But all the vertices here are connected to vertices in L1 and R1, which are almost of size omega n, okay? But not quite omega n, just slightly below. So finding these edges below, I give you this set U and ask you to find a large matching, will require you on average for each edge omega n work, because you're looking for a needle in a haystack here, and so you basically have to go through entire list, on average half of them, before you'll find this edge. But not all is lost, and there is something very hopeful here. If instead of induced matching I told you that the L2 R2 graph is a graph of degree theta d. Okay? That is, vertices here in this, if I look at L2 union R2, have degree theta d inside this subgraph. Then you can actually find an order 1 approximate matching in order n square over d time. Why? Every vertex in L2 could sample order n over d edges at random, and you expect to land order 1 edges inside R2. Since R2 vertices have degree theta d, a typical R2 vertex is getting only constant number of edges. So you are getting a low degree graph between L2 and R2. You run any greedy algorithm, you will recover a constant factor approximate matching now. Okay? So news is bad if L2 R2 looks like an induced matching, but if it starts to be a somewhat denser structure, things get better. Okay? And this is what was formalized very nicely by in the BG24 paper. So they showed that there is a n square over d time algorithm for ISM that returns an order 1 approximate matching, and where d is the average degree in the graph induced by the vertices in the matching you return, not in U. Okay? So d is the average degree in the graph induced by the matching vertices that you return. Okay? That's very important. Okay? So you return a matching, and you also have recording some sort of a proof of why you had to work hard, and that proof is the average degree was small, that's why I had to work very hard here. Okay? And that's the key idea to remember. Okay, so if M is essentially an induced matching, you are not escaping the omega n square lower bound. But when the graph has high average degree, we are getting a non-trivial speed up. Okay? So we have no control over the d that we are going to encounter. But the beauty of BG24 is that they found a way to show that if you're going to repeatedly solve ISM instances over a sequence of updates, total work you do in this task of solving ISM instances can be tied to ORS graph density. So let me show you how this is done. So here is the BG24 algorithm. We are going to process these updates in batches of B. B is going to be much larger than n, but much smaller than n squared. And processing the batch will require us to solve roughly order B over n ISM instances. Every theta n updates, I solve constant number of ISM instances. Suppose T is the total time you spend in solving these ISM instances, then the amortized update time of your algorithm is T over B. Okay, that's straightforward. So here is the naive bound that you can use as a reference, and then I'll show you how they improve upon that. So what's the naive bound? Every ISM instance takes n squared time to solve. So you solve B over n instances, total time spent is B times n. Divided by B to amortize, you get order n after time. Not surprising, that's exactly what we would expect to get if you are doing the naive analysis. Okay, so they came up with a more clever implementation, and if nothing else you take away from this talk, I think you should remember this nice implementation, because I think this is a beautiful idea. Okay, so it's really a tale of 3 graphs. Okay? These 3 graphs you initialize at the start of every batch of B updates. Okay? And the first graph in this tale is this graph G old, which is really the star, going to be the playing the star role in this story. So what is this graph G old? Your batch of B updates is about to start. You look at your current graph G at this point in time. That is your graph G old. Okay? This is going to remain a decremental graph as the algorithm progresses. Over time, it will only lose edges. no new edges are going to make entry into this graph. Okay? How does it lose edges? Well, any deletions which apply to edges in G old, right, during the batch, you will apply them to G old and remove those edges. But there is another way it's going to lose edges. When we are solving ISM instances, if I find a large matching inside G old, I'm going to remove those edges from G old and put it somewhere else. Those edges are also going to be lost from G old. Okay. There is a second graph, which is G batch, which is going to be a fully dynamic graph. So what is this graph? This graph is easy. All the insert deletes you receive during the batch, they are just going here. Okay? If a delete applies to an earlier edge, it goes into G old, but otherwise it just applies. What will be the size of this graph? Well, this graph is going to be order B at all times. Okay? G old could be n square edges dense, but this one will be order B because it's only determined by the batch length. The last graph is G match. It's initialized to be again an empty graph at the start of the batch, and what does it receive? It's going to receive the matchings that you find in G old and remove from G old, you put it in this graph. And you apply deletes in the batch. You know, if some of these edges you added here, they get deleted, you remove it from. Okay. Can anyone tell me what's the size of G match?
The size of the maximum match that you found.
Linear.
How? Linear in what?
And
No, it will be order B. So how many times can matchings be added here? B over n times you solve ISM instances, and every time you add a matching of size theta n. So B over n times theta n, this is going to be just order B. Okay? So this is also order B. So remember, G match and G batch are order B size. Okay? So you have some control on how big these graphs are. You have no control on how big G old is. Okay? Good. So this is how the interaction looks like between all three graphs. G old is the graph G at the start of the batch, and any deletes get applied here, and it loses edges as a result of those deletes. And then whenever you find a large matching in solving ISM instances in G old, you move those edges to G match. Okay? And G batch is just insert delete during the batch. Okay, so how does all this help?
Just a quick question.
Yeah.
So when you delete edges in G old and reinsert them, where do they go? Do they go in G batch?
So when you delete edges, deleted edges are gone.
Yeah, and when you reinsert those. they
When you
go in G
reinsert, it will go in G batch. Yes. Any new insertions are only going to G batch. Yeah. Yes, important. This is a decremental graph.
G-batch is just helping you sort of for the upcoming batch.
Yes, exactly. That's right. And it's basically telling you what new graph is being revealed during the current batch. Yeah. Okay, good. So here is the algorithm. Whenever you need to solve an ISM instance, GU, all we need to do is solve ISM instances because of that reduction I told you. You're going to first run the greedy algorithm on G batch union G match to find a large matching. Okay? These graphs have order B edges. Just run the greedy maximal matching algorithm. How much time? Order B. It's just linear time in the number of it. So nothing smart is being done. But if you fail to find a large matching here, it's time to go to G old. Okay? Remember, ISM promises you there is an omega n size matching. So if you didn't find it in G batch and G match, where must it be? It's a partition across all this. It must be in G old. Right? So now it's time to do hard work, and you look for this matching in G old. you find this large matching M and you move it to G match. So let's suppose M1, M2 to MT as the sequence of matchings you have found in G old in repeatedly solving ISM instances during this batch. And let Di denote the average degree in this graph G old V of Mi when the matching Mi was found. Okay? So what does that mean? The work you did must be N square over Di, right? Because of the opportunistic algorithm. Good. So now we can analyze the runtime. Total time spent in finding all the matchings in G batch union G match is, we'll do this computation B over N time, and every time we spend order B time. So the total time is B square over N. Very simple. Okay. What's the amortized update time divided by B? Is B over N. Okay. So if B is not very large, this is looking good. What about the other work? The work, hard work is happening in G old, which is a dense graph, right? Well, you remove T matchings and the ith matching had average degree Di. This is summation N square over Di. This doesn't seem friendly at all to understand, right? What are those Di parameters? So that's where the magic happens. BG24 shows that summation is bounded by N squared times ORS of N comma theta N. In particular, they show summation 1 over Di is bounded by ORS of N comma theta N. Okay?
This is only for decremental graph that you get the summation. Like I'm trying to
Yeah, it is using the fact that this is a decremental graph that I'm not adding and deleting edges. Yeah. But I'll show you how this is going to come. Okay? So for now, just assume this magical result is true. What does it tell us? Okay? Well, so this means this part will contribute an amortized update time of N squared times ORS of N comma theta N over B. So notice the tension. The top contribution wants B to be small. The bottom contribution wants B to be large, right? So what will you do? Well, you will balance it. And you set B to be N to the 3/2 times square root of ORS of N comma theta N, which will give you the update time that I claim. Okay? And so once again, if ORS of N comma theta N turns out to be N to the small o of 1, you will get N to the half plus small o of 1 update time. Okay, so let me show you the magic, which is that result connecting it to ORS graph density. Okay, so the lemma is summation 1 over Di is bounded by ORS of N comma theta. Okay? So here is the idea of the proof. So you find these matchings M1 to MT in G old, and Di was the average degree in V of Mi at the time when Mi was found. Okay? Construct a new graph by sampling these matchings at the following rate. Sample matching Mi with probability 1 over 100 Di. Okay? Roughly inverse of the degree that existed. Okay? So if Di is small, you're almost certainly keeping the matching. And if Di is large, there's a small probability you're keeping. What you can show is that these sampled matchings, they form basically an ORS graph in reverse. If you see them in reverse, so if the prefix is, instead of prefix you look at suffixes, you're going to get an ORS graph. Okay? So let me show you the idea in a bit more detail. Okay? So let's imagine, for simplicity, this captures the crux of the argument anyway. Let's imagine all the degrees were roughly the same. They were within constant factor of each other. Okay, d1 to dt were roughly just same quantity d. You can do geometric grouping and then apply this argument otherwise. Okay? Now, where we sample a matching MI, I want to argue, after I'm done sampling all the remaining matchings, MI is going to look more or less an induced matching with respect to all the edges in Mi plus 1 to M sub t, the suffix. Okay? Why is that? Well, what was the degree when Mi was found? It was, average degree was D. Just think, instead of average degree, it's the max degree. Okay? Look at an edge UV in Mi. It has order D edges incident on it, U and V each of them. The future matchings could be using these edges, but you're sampling them at rate 1/100D. So for a typical edge UV in Mi, no edges incident on U and V were sampled. Okay. You may get a few violations to this, but then we do a cleanup. We discard some of these violated edges from Mi. The matching size may go down by a factor of 2. It will still be a large induced matching, and you will get a large ORS score. Okay. That's it. That's basically this beautiful idea that's connecting it to ORS graph density. Okay, so in the remaining time, I'll just spend like few minutes really to tell you about the ideas that go into our improvement. There is a complicated recursion to deal with, but the idea of the recursion is very easy to explain. So I'm going to just explain that. Okay.
Sorry, question.
Yeah.
A small question.
Yeah.
The argument that you mentioned, it uses the suffix to be.
Yeah.
But is there a way you can change the argument to say it's for the whole sequence?
No, not. Okay. I will address that point. There is not a one-line fix to that. I'll address this point towards the end. Okay, but no, there is not a simple one or two line idea that will allow you to claim that. Yeah, it was in fact not clear at the time when Sohail and Alma's result came out, and then we worked. It was not clear because that will connect it to RS graph density, right? Yeah, but I'm going to tell you something about it a bit later. Okay, not much later. Okay, so the first thing we do, we strengthen the opportunistic algorithm of BG24. Instead of n square over d, we are getting m over d, where m is the number of edges in the graph. Okay, and instead of d being average degree, we get something stronger, which is very useful when you are trying to use these ideas in a complicated recursion. The stronger property is d is really the max degree. Okay, so no, you won't have to deal with the fact that some vertices could be much above this average degree boundary. Okay, this is not at all difficult to do. It's just like useful thing to do. Okay, so m over d is not going to help you if m was n square, but m over d is a useful thing if somehow you knew m was not large. Okay, and keep that in mind that when m is not large, this is a better bound to work with. Okay. Okay. So I'm going to define a family of algorithms, and each, successive algorithm will be better than the previous one. So the first algorithm is algorithm A1. What does it do? We just take the BG24 algorithm and replace their opportunistic algorithm with our opportunistic algorithm. And now if you did the balancing, you will get, if m was the number of edges in the graph, you will get root m over n times ORS of n comma theta. And sanity check, if m is equal to n square, you got BG24 result. But if m is better than n square, much smaller, you will get a better uptake. Okay, good. So nothing new has happened so far. Let's now deploy this in a more clever fashion. Some of you might already guess what it would be. Here is algorithm A2. Same setup, same three graphs. Whenever we want to solve an instance of ISM, before we were running the greedy algorithm on GBatch and GMap. Now we are going to run this new algorithm A1 there. Okay. Why run greedy? You know there is a better dynamic algorithm. We are going to run. Those graphs are fully dynamic, and we are going to use our new fully dynamic algorithm on those graphs. Okay. So I'm going to run A1 on GBAT and A1 on GMAT. Okay. If either of them succeeds in finding a large matching, I'm happy. If not, I go back and do the hard work in GOLD as before. Okay. What is M in GBAT and GMAT? It's B, and B is going to be chosen to be something distinctly better than N squared, so you can see seeds of some improvement. Yeah.
So the running time of A2, because now it runs A1 as a subroutine, it will increase.
Running time of?
A2
Yeah.
will be more than the original running time A1. Because it uses A1 itself as a subroutine.
Yeah, but A1 is better than the greedy algorithm that you were using
That's
before. Yeah, so we should see what it leads to.
So you get a better approximation bound, but also worse running time for each update.
No, we get the same approximation. We are always going for 1 minus epsilon approximation, and our update time is going to be better
Okay.
because I will be able to handle a bigger batch size. So let me show you. Okay? So now we are running a better algorithm on GBAT and GMAT than the naive greedy algorithm. We can actually use a bigger batch size. And remember, there was a tension between B, right? The reason B couldn't be chosen to be too large was because I was getting this order B over N update time term because of running the naive algorithm. But now I have the square root B over N kind of a behavior that I'm getting. So if you balance it now correctly, B can be set to be N to the 5/3 as opposed to be N to the 3/2. Okay? And the update time becomes N to the 1/3 times ORS of N comma theta N to the 2/3. And you can continue this process. Next time, A3 will run A2 on GBAT and GMAT and so on. And ultimately, the final algorithm AK will give you N to the 1 over K plus 1 times ORS of N comma theta N to the 1 minus 1 over K plus 1. So in the limit, this is giving you N to the small o of 1 update time times ORS of N comma theta N. Okay. So you have to pay attention to you lose at every level of recursion on the quality of the solution and stuff. So you have to pay attention to constants and stuff. But the idea itself is very simple. Okay. Okay. So let me conclude with some final words. So what we showed was there is an algorithm for maintaining 1 minus epsilon approximate fully dynamic matching, whose update time is now tied to settling a combinatorial question, namely understanding density of ORS graph. Okay? And of course, as Sagnik was asking, right, is there a way to relax this, prefix or suffix induced property and just make it induced with respect to the whole thing? So at the time when we obtained these results, we didn't know the answer to this, but now we do. Earlier this year, Kevin Pratt showed that density of ORS and RS graphs is essentially same. Okay, so if you had a dense ORS graph, you will also have a dense RS graph. Okay, you lose a little bit in the parameters. The matching sizes, the size of the matchings will change and so on, but it will remain constant, omega n. Okay, so all those results can now be restated, replacing ORS of n comma theta n with RS of n comma theta n. And this is very good because RS graph density has been studied for decades, so it's on a very strong footing. We know, this is kind of a problem where there won't be an easy resolution, and at the same time, there is a good chance we feel that the answer could turn out to be much better than n. But ORS graphs, we didn't quite fully know what relaxing this induced requirement with respect to prefix or suffix meant. Maybe it immediately makes it easy to, in few years we might have shown that you can pack close to n matchings, okay? But now we know that's not going to happen. Okay, so the question I started with, it's still on table. Is there an unconditional, right? So this is a conditional dream result, but is there an unconditional fully dynamic 1 minus epsilon approximate matching algorithm which achieves an update time of n to the 1 minus omega 1? And or conversely, can we show some conditional lower bound on the update time which says that, update time needed to maintain 1 minus epsilon approximate matching really is tied to ORS or RF graph density. Okay? There is no escaping this connection. Right? And so that's all I wanted to say. Thank you. Yeah.
Can you say a little bit about how the opportunistic algorithm
Works? Yeah, it does something very simple. It basically, so you have U.
Barna Saha. Professor Saha is the Harry E. Gruber Endowed Chair Professor of Computer Science and Technologies at University of California, San Diego, and also the director of the Encore Institute. Professor Saha earned her PhD from University of Maryland College Park in 2011 under the advice of Samir Khuller, after which she became the senior research scientist at AT&T Shannon Research Laboratory. Before joining UCSD, she was a tenured associate professor at UC Berkeley and at UMass Amherst. Professor Saha's research in algorithm design and fine-grained complexity has been recognized through multiple awards, including the Presidential Early Career Award for Scientists and Engineers, and the prestigious Sloan Fellowship in 2019, and the Young Alumnus Award from IIT Kanpur in 2020. Professor Saha is also the founder of several community initiatives like TCS Women and TCS for All. So join me in welcoming Professor Saha. Over to you.
Thank you, Nija, for a very nice introduction. So it's great to be here. So I'm going to talk about fine-grained optimality of dynamic shortest path. So it's going to be about shortest path, dynamic shortest path, and I'm going to talk about lower bounds. And whenever there is fine-grained in front of it, that means it's like going to be conditional lower bounds based on certain conjectures which are popular in fine-grained complexity. So this is a joint work with Virginia Williams, Injan Su and Christopher A. Injan is a postdoc at UCSD. He got his PhD at MIT under Virginia. So he is in the job market. So if you're hiring, you should hire him. He is great. And Chris is my student. He's not in the job market this year, but he will be in the job market next year. So you should just keep an eye on him. And during the presentation, you will see a lot of hand-drawn pictures. So those are all drawn by Chris. So anything that you see not hand-drawn is mine. So you can assign credits accordingly. So you will be assigning more credits to Chris, actually. You'll see more hand-drawn things here. Okay, so anyway, so this talk is going to be relatively short and simple. So hopefully you'll understand everything. If you don't, So we're going to talk about single source shortest path. So just we are given a weighted graph. It could be directed or undirected, and a source vertex S, and we want to find distance from the source vertex to all the other vertices in the graph. So this delta SV denotes the distance from S to V. So obviously you can solve it using Dijkstra's, and that takes about n plus n log n time. So in recent years there has been even improvements over it, but that for this talk you can think about order n is Dijkstra's algorithm. Now we are interested in the dynamic shortest path. So in the dynamic regime, so we have G is undergoing edge updates. So edges can be inserted. Then edges can be both inserted or deleted, or you can think about the partially dynamic setting, where edges can, if edges can only be inserted, then that's incremental, and if the edges can only be deleted, then that's decremental. And here our goal is to minimize update time. Okay, so it could be either worst case or amortized. So what could be a very naive algorithm? The naive algorithm will be to just run Dijkstra after every update. So that will take you order of n graphs. So if you are looking at a total of m updates, like over all the edges, then the total work or time required is order n squared, which is order n to the power 4 for dense graphs. So if you are running your Dijkstra again and again. So the main question that we are asking here, whether there exists an algorithm for this dynamic single source shortest path with a total update time which is better than just running this Dijkstra again and again. So can you have an algorithm that has a running time like n to the 4 minus epsilon for dense graph, or n to the 2 minus epsilon for over m updates? And why m updates? Like, because if you are thinking about partially dynamic, right? So in the incremental setting, you are thinking about, you are starting with an empty graph and then the edges are arriving one at a time. So your m edges will be arriving. Similarly, if you are thinking about decremental, then you are starting with m edges and then one by one the edges get deleted. So it just makes sense to talk about m updates. So what is known in these regime? So back in 1981, which is like over 40 years now, so for unweighted graphs, so Ivan and Hewlett, they gave a partially dynamic SSSP algorithm that has a total running time of order of mn over m objects. So if you are amortizing over m objects, so the per update running time is order of n, and that's more or less optimal, because if you think at every step you have to return your distances to all the n vertices from the source, then that's what you would need. Very recently, in 2023, so that's for partially dynamic, incremental or decremental. Very recently, in 2023, and another point to be noted, this is for unweighted graphs, okay? So therefore, unweighted graphs, there is a fully dynamic algorithm which has a running time better than n squared, okay? And that uses some algebraic methods. And there are many works on approximate 1 plus, like, which gives you not the exact distance, but 1 plus epsilon approximation of the shortest path distance. In the partial and fully dynamic setting, there are too many of them for me to cite here, but Thachapal is here, Danupan is here, so you can just ask them, and they can probably fill you in about these approximate computations. Okay, and if you think about all pair shortest path, then for all pair shortest path, there is again a classical algorithm which has order of n square update time, amortized update time per update. And for IISc, this is again like this is optimal. So for IISc, we kind of know what is optimal, and that's in a fully dynamic setting. So given all of these, what we see that there has been no progress if you are thinking about exact partially dynamic single source shortest path. Or fully dynamic, so whatever like dynamics single source shortest path on weighted graphs. Okay, so on weighted graphs, we really, and if you are considering exact computation, we do not know anything better than just running Dijkstra again and again. And that also holds for not just a single source shortest path. If you think about, there is a source on the target S and T, and I'm just interested in returning the path from S to T, shortest path from S to T, so that's your ST shortest path. Even for that, in the weighted graphs, in the dynamic setting, nothing much is known. So forget about fully dynamic, even in the simplest setting of incremental or decremental, nothing is known other than running Dijkstra eigenenic. Okay, so whenever you cannot make progress in algorithms, the next thing that you try is to show lower bounds. So people have worked on showing lower bounds for partially dynamic single source shortest path. So what kind of results are known? Again, these lower bounds, as you will see here, these are like conditional lower bounds. They are based on certain other problems being heard, conjectures on being heard, and then based on that you show lower bounds for dynamic SSSP. So Rodity and Zwick, they showed that if you, the total time required for single source SSSP, partially dynamic, either incremental or decremental, is at least n cube. Okay, so at least n cube, and that's over n updates. So what are the drawbacks of that lower bound? Is essentially it doesn't rule out that it is possible, like there are n costly updates, and after that the updates are much cheaper. Okay, so overall, like there are m updates, right? So n updates could be requiring n cube time, but maybe after that all the updates are cheaper. So overall your total time is still n cube. Okay, so that doesn't tell you that whatever your Dijkstra is doing is the best possible. So there could be a better algorithm even if this lower bound holds. Then there is a more recent result. So this is from 2004, I think. So then there are more recent results which gives you a total time of n square, basically ruling out that you cannot do anything better than Dijkstra. But that only holds when the graph is really sparse, right? When m is like n to the, like m is about order of n. It only holds when the graph is sparse. Otherwise, so that lower bound doesn't extend beyond that. And for sparse graph, actually showing such a lower bound for single sources shortest path is actually trivial, because your total output size over m updates is going to be order of mn, right? So, and if your m is n, so then that follows directly. But that lower bound actually works for ST shortest path. So that's kind of the non-trivial part over there. But it only holds for the sparse graph. So these are kind of evidences like that shows indeed exact computation of SSSP even in the partial dynamic setting is likely hard. Okay. So what is our result? Our result kind of is.
What in the last slide? What is K-cycle conjecture?
So the K-cycle conjecture basically tells you that finding a K-cycle in a graph of with m edges requires m squared time. But that graph is very sparse. That the conjecture is only for sparse graphs. So our main result is basically to overcome these kind of drawbacks of these lower bounds. So what we show that under this minimum weight 4-click conjecture, computing partially dynamic STSP, so not just SSSP, so just ST shortest path, over undirected graphs, so doesn't have to be directed, over undirected graphs, weighted, requires a total time of n to the 4. Okay, so that kind of rules out anything better than Dijkstra, and so this n to the 4 over m updates. And this also holds for any kind of density, so it's just not for, so n to the 4 is for dense graphs, but it also holds for any kind of density, and it gives you a total time of m squared. These are over m updates, okay? So the takeaway is recomputing Dijkstra after every update is essentially optimal. So from this result.
Two questions. Is this for weighted or unweighted?
Weighted, yeah. So and these are mine, right? So that's why you are seeing all these kind of gaps here. So not by crease. So this weighted and over M updates.
And the pre-processing time is anything or?
Pre-processing time is anything. Yes. Okay, so what is this minimum weight four-click conjecture? So the minimum weight four-click conjecture basically tells you that over n node weighted graph, finding the minimum weight four-click, where minimum weight is just a sum of the weights of the edges in that click, requires you essentially into the 4 time. Okay, so that's your minimum weight four-click conjecture. So this is a generalization of the minimum weight triangle or APSP conjecture actually. And this has been widely used in fine-grained complexity. Okay, so we are going to base our lower bound based on this conjecture. Okay, so we'll start with the lower bound, which is for the fully dynamic ST shortest path, and then we'll slowly modify it so that at the end we have a lower bound for ST shortest path, but for the partially dynamic setting. Okay. So we have G, which is a weighted undirected graph over n nodes. We are assuming G is 4-partite. So this is without loss of generality. Okay. So you're considering, so if you have a graph G, you just replicate the vertices this A, B, C, D, and then you are adding these edges. Whenever there is an edge between two vertices, you just add corresponding edges from A to B. So without loss of generality, you can assume that G is 4-partite. And we are also assuming G is complete because we are interested in finding the minimum weight for click. So you can assume this is complete. Okay. So we want to find the minimum weight for click in this graph G, and we will be doing so by constructing an dynamic STSP instance. Okay. So here is our construction for the dynamic ST shortest path. So we have S and T, and for each of these parts A, B, C, D, we are creating these 2 parts here for A, for B, for C, and then we are replicating the part A again in A prime. Okay. So between A and B, we are adding all the edges that exist between A and B here, so we are adding all the edges over here, and their weights are corresponding whatever the weights are there in the original graph. Okay. So similarly between B and C, we are adding the edges whatever exist here in this graph, and the weights are whatever the weights in the graph, and again same for C and A. Okay. And from S to A and T to this last part of A prime, we are just adding edges, and these edges, they don't cost anything. Okay. So now between these 2 parts of B, what we are doing? Okay, so we are now considering, so we have A, we have B, we have C, like we have added the edges AB, A to B, B to C, C to A. Now what we are doing, we are considering, we are going over all the vertices D in D. Okay, and as we are going through each of these vertices, this small d in D, we are updating the edge weights in B and C gadgets. So here, so what we are doing here, so if we are looking at these 2 parts of B, so from the same vertex here in B to this other same vertex in B in this other part, we have this edge with a weight of BD. Okay. And as we are going through D, so what we will be doing, we will be updating this edge weight. So initially, whatever the D we start with, we add these edges, we put the weights as weight of B to D. Okay. And similarly here, like we add these edges. So this is the dynamic part. Initially we had all these edges, these black edges here, and the black edges here. Now we are going over the vertices in capital D. For every D, we are adding these blue edges and the green edges. So these are going between the same vertex, same B here, same D here. Okay, so these are like a matching here. And we are updating the edge widths to BD. Okay, so that means you start with the first D, you add these edges, then you consider the next D, then you delete these edges and again reinsert with the appropriate weight. Okay, so that's what you are doing for D. And then as you are going over D, so D is kind of in the outer loop. Now in the inner loop, you are looking at all the vertices in capital A. So here, you have to add the edges for weight AD. So again, you are adding this only one edge from A to G with a weight of AD over 2. Okay. So similarly over here, just adding one edge, A to D, AD over 2. And when D changes or A changes, you delete it, you reinsert another edge. Okay. So that's what you are doing. Those are your dynamic updates. So as you see, you have to insert edges, you have to delete edges. So this is kind of the fully dynamic model. Okay, so that's your construction. So after doing this, you are querying. So after adding, so for every A, once you have added this edge in A and A prime, and whatever the previous edges you have deleted, you are querying for the shortest path from S to T. Okay, so that's your query after every A. Okay, and the claim is like this shortest path when you are querying it, so that gives you the minimum weight for click containing the edge AD. Okay, so that's not very difficult to see. So if I am looking at the length of consider any ST path here, right? So if you are looking at the length of the ST path here, so obviously here you have just one edge A to D, like A to A, like so that weight has the weight of that edge is AD over 2. So you are going from A to A, right? And this edge exists only for the particular A you are considering. After that, you are going from A to B. Then you are following the same edge B to B, right? That has a weight of BD. And here again, like from B to C, you are following the same vertex C to C, because those are the only edges exist. Then here, only this edge exists for the particular A, right? So that's why you have to choose the same A, whatever you have started here with. So there is no other choice for A over here. So you go to the same A and you complete it over here, right? So if we add up the weights, so you see that gives you the weight of the clique containing AD. And obviously you are going to select the minimum weight paths that will correspond to the minimum weight for clique containing AD. Okay? So if you are doing this over all the ADs, ultimately you will find the minimum weight for clique in the graph. Right? So then how many queries have we made? So for every, how many updates have we made? So for every D, we are doing order and updates in BNC because we are looking at all these B's and we are updating the edge weights, right? So B1D, B2D and so on. And similarly here, so here we have done order and updates. And so and for every A, we are just considering one edge. So that's just order one updates for A and A prime. So overall, so we have n square updates, right? Like for every D, order of n, so n square, and in the inner loop, for every A, I'm doing order 1, so overall again, like order of n square. And the number of queries is also for every AD, so we have n square queries. And by the minimum weight for clique conjecture, this will require your total time of n to the 4. Because that's your conjecture. By doing these n square queries over n square updates, you are able to detect the minimum weight for clique in this graph. So these n square queries will require you n to the 4 time. So that gives you the lower bound for the fully dynamic setting. Okay? So there were quite a few parts where we utilized the fully dynamic here, right? In order to ensure that whatever A is chosen here, the same A is chosen over here as well. We just had one edge, right? So that was crucial. And also over here, we are adding and deleting, right? Like updating the weights means we are at whatever the edge has been there, we have deleted it, and we are adding the same edge but with a new weight. And that was also crucial in order to give you the right weight. So those are the two parts where fully like insertion and deletions are both utilized. So now we are going to look at like, we'll slowly modify it so that we have a lower bound for the partially dynamic setting, and we'll just consider the incremental setting for now, okay? So first we are going to modify it so that we will just allow insertion, but the graph will be multi-graph. So this kind of a lower bound for multi-graphs for partially dynamic ST shortest path, okay? So if we have multi-graphs, so that will be the first step, and after that we'll see how to remove this constraint of having multiple edges between two vertices. Okay? So this is how the lower bound looks like. So we consider this capital M, which is take a capital M to be sufficiently large, so larger than the weight of any forklift, okay? So which means like 6 times whatever the highest weight you see on the edges. So consider your capital M to be larger than that. So now what we are doing, so we can only allow insertion of edges in B, right? You can only allow insertion of edges in C, and the same for A's. So what we are doing, like in B, again like we will be considering, so we have the same construction, like same like 2 parts for A, 2 parts for B, 2 parts for C, and 2 parts for A prime. We will be going over each D, but now we go through these D's in decreasing order. Okay, so you consider if there are n vertices in D, you start with the nth vertex in D, then n minus 1, n minus 2, and so on. So we consider D in decreasing order, and we are adding these edges here, like again from B to B, but this time the weight of that edge is capital N times D plus weight of BT. Okay, so what is the intuition here? The intuition here is that when you are going, as you are going through D in decreasing order, right, as you choose a smaller D, so that smaller D edges will be favored. Because otherwise this is like just too much. So you will never be considering edges over here for higher D. So whatever the new edges you are inserting for smaller D, those will be favored. Okay? So that's what you do here. So MD plus weight of BD. So in C, you will also do the same thing, MD plus weight of CD. Okay? So that's kind of the changes in B and C. You do something similar for the A as well. So now you only keep adding edges, so you are not going to delete edges. But you have to make sure you favor whatever A you are considering, you favor that A, and whatever D you are considering, you favor that D. And you do so by appropriately adding these extra weights here. Okay, so you do m squared over D, that means whatever the current D, that is favored, you do m times A. So after D being favored, whatever is your current A, that should be favored, and then you have the weight of AD over 2 here, and weight of AD over 2 over here. Okay? So why is this a multi-graph? Because you are adding these edges over here, right, like B to B. So for every D, if there is an edge from B to D, you will be adding, the first weight was like n plus weight of BD, then the second weight will be 2n plus, the first weight is n, D is n, so n times n plus weight of BD. Then when D becomes n minus 1, you are adding n minus 1 times n weight of BD, this another edge, and so on. Okay? So your B and C will be multi edges. Okay, so at the end of it, you will be querying your delta st, the distance from s to t. So again, there are n square queries, n square updates, and following the same logic, like the shortest path distance from s to t will be your minimum weight for click containing the edge AG plus these additional weights, which you can obviously discard in order to find the minimum weight for click over your entire graph over n square queries. Okay, so that's so now you are only using insertion, no deletions, but your graph is multi-edge. Like it's not a simple graph anymore. Okay, and generally when you have this kind of lower bounds for multi-graph, the way to convert it into a simple graph is you consider the multiple edges, you insert a vertex for each of these multiple edges, right? But that blows up your vertices too much here, so your lower bound will not hold. If you want to convert your multi-graph into simple graph by doing that kind of a straightforward modification. Okay, so this is, any question? Okay, so this is just the total time over n square updates and queries is n to the 4, again because you are finding the minimum weight for click over here. So your amortized over the n squared updates is n squared. And another thing to be noted here, so this is like, I'm showing you the lower bounds for dense graphs, right? Like n squared update, like n to the 4 total work time. But all these constructions here, like this works out for any density, because the number of edges that you have here, number of edges that you have over here, and all the additional edges that we have added is really order of n. Okay, so this construction actually works for any density. Okay, so now I will show you how to convert this multi-graph into a simple graph. Okay, and that will be kind of the end of the construction. Okay, so where does the multiple edges come? And I'm just looking into the B gadget right now, because the same thing you will be doing for the C gadget and the A gadget. Okay, so again going back, so for the B gadget you had these two parts. You were adding these edges for every D, MD plus weight of BD, right? We are doing the same thing for C and slightly different, but just slightly difference in weights for the A gadgets, but they are basically the same. So it will be whatever the modification I'm showing you for the B gadget, you will be doing the same thing for A and C. Okay, so consider the B gadget. So let's think about, let's take this example. So you have this D and you have this B. And these are your vertices numbered from 0 to 3, 0 to 2. So you're considering B in decreasing order, right? So you'll be considering your green edges first. So in the original construction, so it's from 2, the edges go from 2 to 3, 2 to 1. So this is going from so first of all you add these edges for this B, right? So this is going, this is the first vertex. So first vertex to first vertex, third vertex to third vertex for D equal to 2. After that you are considering the red edges, so you are adding these red edges. And then finally you are considering the black edges for D equal to 0. And you are adding these black edges, right? So this is how your B gadget looks like in the original construction. So now we are going to change that. So how do we change it? We add a middle layer of 2n vertices. Okay, so we had 2 layers for B. Now we are adding another additional layer with 2n vertices. And so we look at the green edges. So previously the green edges were going from 1 to 1 and 3 to 3. So now the green edges will go from 1 to 1 via this middle node, which is B plus D. So B here is 1 and D here is 2. So B plus D is 3, so you look at 1, 2, 3, so the third vertex. So you go from 1 to 1 via this third vertex. Okay? So that's kind of the modification we are doing. So if you're looking at here, B is 3, B is 3 and D is 2. So you'll go from 3 to 3 via the fifth vertex in the middle layer. Okay, so you're adding from the first vertex B to the third vertex in the third layer to the same B, but you are going via B plus D in the second layer. Okay, so initially if you have, when you have added these green edges, obviously this is the only path you will be following, right? So previously when you were following this green path, here you will be following the same green path. So if you are entering through one, you will be exiting through one. That's kind of the property we want to maintain. That whatever we are entering, we exit through the same vertex, because ultimately we want to consider the same A, B, C, D, right? So here also, if you are entering through this purple vertex, you will be exiting through the purple vertex. So after that, you are considering the red edges, because you are going in a decreasing order over D. Okay, so one thing I have to say, like what weights do you add to these green edges? So you add whatever the D you have considered, D plus 1 times this N plus weight of BD over 2. Okay, so let's go back. So we are adding these edges from B to B plus D and then going back to B. And the weight that we are adding is D plus 1 times capital N plus weight of BD over 2. Okay. So which again tells you, like, initially your green edges will be favored. After that, when you are adding the red edges, so red edges is for D equal to 1, so like 2m plus weight of BD over 2. So those red edges will be favored over the green edges. Okay. So here again, like you are going from B to B, but via B plus D. So what happens here? Like first of all, if I'm coming from 2 here, I go over here, I want to exit through 2, right? If you try to exit through green, you will be paying much more because the weights of these edges is much higher, right? So there is no incentive for you to consider edges that have been of other colors that have been added earlier. So if you are considering red edges now, you will be just whatever red edges you have entered through, you will be exiting through the red edges. And the other thing to see here, that all these red paths that we have created are all vertex disjoint. By considering this going through B plus D, all the red paths are vertex disjoint. So there will be no confusion, there are no 2 red edges here, just one red edge to follow. So essentially these are the 2 properties you want to maintain. You will be always going via the latest edges that you have, latest colored edges that you have added, right? And which should ensure that you are entering and exiting through the same vertex. And that's being achieved through this construction. So after the red edges, you will be adding these black edges, and now the weights of these edges is again D is 0, so it's N plus weight of BD over 2. Okay. So once you add the black edges, whenever you have an option through black edges, you will be following the black edges. And all the black paths are vertex disjoint. Okay? So that's it. So that's what you are going to do for every gadget. So all same color paths are vertex disjoint, and shortest ST path will never mix colors. Okay. So that kind of ends the construction. So overall, like this is how your entire construction looks like. So you have started with these 4 partite graphs. You have created these 5 parts. Inside each part, now you will be replacing these with this new gadget, right? These 3 layered gadgets, and that's it. So overall, you have n square updates and queries, and since this detects the minimum wait for click, the total time will be into the 4, and that gives you the lower bound, and it holds for any density. Okay, so what is the time now? 20 minutes, I'm done actually. Okay, which is good,
Let me
right?
ask, like, so,
Okay.
like, what's the trade-off? Like, you could have picked like 5 clique or k-clique. The number of vertices blows up, or so you could have used a stronger conjecture like a k-clique and repeated the gadget.
So if you are considering, yes, so the number of vertices will blow up, right? And yeah, there is nothing to be gained by considering higher cliques.
Trade-off doesn't work.
Mhm.
What
Yeah,
would
so here you are already getting into the 4, right? So if you are considering higher cliques, yeah, so the higher cliques doesn't work. Yeah, simply the constructions for higher cliques doesn't work. So we also looked at, in this work, we also looked at some variants of shortest path. So one of them is node-weighted shortest path. So in the node-weighted shortest path, you have weights on the nodes, and your minimum, and the path that you are trying to look at is the among all the paths, which is the total weights on the nodes to be minimum. That has also been studied quite a bit, and there's an interesting version of shortest path. So if you consider the all-pair shortest path version of it, the node-weighted version of it, so there is an algorithm that runs in time better than n cube. Okay. So there is bottleneck path. So what is bottleneck path? So here you are trying to find a path which minimizes the max weight of edges in that path. Again, bottleneck path is another problem. So here, if you are considering the all-pair version of it, there is an algorithm that beats n cube. Okay, so these are the, and basically, so for all of these, instead of, so for all pair shortest path, you will have mean plus matrix multiplication. So for node weighted bottleneck path, you will have different variants of matrix multiplications, and those you can compute in time better than n cube. So we try to look at this node weighted shortest path and bottleneck path and try to see what can be said about these problems in the dynamic setting. So all these variants, they are all pair versions in the static setting, have less than n cube running time. And for all of these variants, interestingly, we give incremental algorithm, which has running time like n to the 4 minus epsilon total time. Okay, so for all of these, we can beat the n to the 4 trivial bound. And even more interestingly, if you look at these running times that we get, this is like n to the 3.915, 3.686. So that tells you that these are using fast matrix multiplication. Okay, so these are all algebraic algorithms, like the incremental algorithms that we have are algebraic in nature. And it's actually the algorithm is actually very simple, that uses the all pair version, the static all pair version, and whenever you have edges inserted, you consider some matching of the inserted edges. So you consider, so that you can take the inserted edges and follow the whatever, like the all pair. So you compute all pair version before starting a batch of insertion. Then you do some batch of insertion, and you are basically, you either take this inserted edges or whatever you have computed for the all pair version before the batch of insertion started. You can alternate between those versions, and you will be able to compute the shortest path. So I'm not going through it, but the algorithm is actually very simple. And since the all pair version uses fast matrix multiplication, these algorithms also use fast matrix multiplication. So a natural question to ask, whether this fast matrix multiplication is really necessary or not. And here we show, if fast matrix multiplication is not allowed, then again you cannot do anything. Okay, even in the partially dynamic setting. So, and the outcome, so here the result follows from combinatorial 4-clique conjecture. So here there is a, so Anupana was asking about this pre-processing. So here, like there is some conditions on pre-processing. Obviously for incremental algorithm doesn't really matter, because you're starting with an empty graph, what are you going to pre-process? For decremental graphs, there is a question about pre-processing and the 4-clique conjecture. doesn't hold with preprocessing. So we do have another conjecture like OMV3 conjecture based on which we can avoid preprocessing. But anyway, so like under the combinatorial 4-click conjecture, we show that any partial dynamic node-weighted shortest path or bottleneck path algorithms requires n to the 4 time. And what is the combinatorial 4-click conjecture? It basically tells you that if you are not using fast matrix multiplication, then finding a 4-click, not the weighted 4-click, just the 4-click requires you n to the 4 time. Okay. And if you look at the lower bounds, again I am not going through the lower bound constructions, but they are very similar to what I showed you for the shortest, single source shortest path, ST path, shortest path. Okay. So for example, for the node weighted shortest path, like I do have the weights on the nodes and they are fixed. Edges are getting inserted and deleted, right? So in the incremental setting, edges are getting inserted. So I have to modify my B gadget. So previously my B gadget looked something like this, like you have these 3 layers, right? You added this edge from B to B plus D, then B plus D to B back, right? Here, and there are weights on these edges. So these weights kind of ensure that you always prefer the edges that are being added at the end. But now the weights are on the vertices and these are fixed, right? So but you still have to ensure that whatever the edges you are adding, so you are again adding the edges in the same way, B to B plus D, B plus D to B. Okay? But you have to now ensure that whatever the latest edges you have added, you are going to prefer that. Okay? So to do so, we just modify, we just add weights properly like on these vertices so that kind of these last edges, latest edges are preferred. Okay? So for all these weights on these vertices, these are kind of proportionate to these j's. Okay, and here they are proportionate to minus 4 and minus 2j. Okay, so what does that mean? And here also we flip the order in which we consider d. So previously we were considering d in decreasing order. Here we consider d in increasing order. Okay, so by considering e, it doesn't matter much, but considering d in increasing order. So if you are looking at a particular j here, so because the weight here is 4n minus 2j, so we'll try to take an edge which is as low as possible. Okay, and then once you have taken this edge, you want to go up as high as possible because here the weights are proportionate to j. Okay, so and this kind of ensures that if these dashed edges and the latest edges, you are really preferring this dashed edge over whatever you have added previously. So just by modifying the weights on the vertices, you kind of simulate the same behavior, that the latest edges are being preferred and these latest edges are all vertex disjoint. Okay, and once you have that these two properties, you can just get the same lower bound. And since here ultimately you are trying to detect whether there exists a 4-click or not, ultimately your lemma will look something like that. Like now you have considered these node weighted versions, so you have the weights on the nodes, right? But the edges don't have weights because your original graph didn't have any weights. But in your dynamic setting, if you have a path whose total node weight is less than something, then there is a 4-click, otherwise there is no 4-click. So that's kind of the ultimate lemma that you will be proving, and that gives you the lower bound. So just some final thoughts on open questions. Just from our work, these are like immediate open questions. For example, we have for the incremental setting, we have node weighted shortest path and bottleneck paths. We give algorithms better than n to the 4, but we do not know how to do it for the decremental setting. Again, the incremental setting algorithm is very simple. Since we can compute all pair bottleneck path or all pair node weighted version in less than n cube time, we use that, and then we use some batch insertions, and we can just go over these two phases, and we can have a better incremental algorithm. that paradigm doesn't work for the decremental setting, and we do not know whether this decremental setting is hard or whether there exists a better algorithm for this problem. So that's kind of an immediate open question. And also for the bounds that we also have some lower bounds. So we do have some lower bounds of n to the 3.5 and omega plus 1 for these problems, but they don't match with our incremental algorithms. So essentially, we do not understand these two problems, these two versions of the problems very well at this point. And for the single source shortest path or STSP, like there is this recent work which gives you for the unweighted version in the fully dynamic setting, it beats the n square update time per update or n to the 4 update time for total update time. And so obviously we do not have any lower bounds for the unweighted version, and it's unlikely whatever they get is the right answer. So there is an open question over there. So provide non-trivial lower bounds for the unweighted version or get a better algorithms. And they must use algebraic methods, because in the fully dynamic lower bound that we have, if we consider combinatorial algorithms, then actually we can show for the unweighted version there is nothing better. So the unweighted version, in order to get anything better, you need algebraic methods. There already exists an algorithm like that. Question is like whether you can improve it or give some non-trivial lower bound for it. Okay, so that's it.
So just following up on Siddharth's question, let's use 5T. I think we still get some lower bound, just like it's a weaker bound. Yeah, I think something, but not as strong as.
Yes, you might get like, yeah, so you won't get this trade-off, like you might get something weaker. Yeah, it doesn't help. Yeah, there is this sweet spot at the 4 clicks, like here. So there were previous lower bound which is based on a PSP that got stuck because it's kind of it was again a very simple lower bound. Like you have this entire graph, then you add a source vertex, and then you add some edges. Like again, so weight of like so NW plus 2NW, 3NW, something like that. So that essentially you add one edge and then you kind of, so you do nothing over your actual graph, and just based on these n edges that you add sequentially or delete sequentially, you can find all the all pair shortest path. So that's why their construction was kind of stuck at n queries. So from triangle going to 4 click actually helps, but from 4 clicks there is nothing much to be done considering k clicks.
So when you say that you're not allowed to use algebraic methods, I mean, how does that statement?
Yeah, but
like, what's the formal?
there is I think I don't know. So there is that definition is kind of iffy. We generally don't allow fast matrix multiplication. I don't know if you guys have any other better answer to it.
No, I think, but
Yeah.
like there's no definition, I think.
Yeah.
But I think the way that probably they are using it is they're changing the conjecture. So the conjecture itself is some combinatorial conjecture.
Yeah, definitely, right? Even for Boolean matrix multiplication, right? Like we're saying combinatorial algorithm requires n cube, but obviously have n to the omega. So that's. Any other question?
We have a photo session, no free lunch, so please smile for it. It'll be right outside in the garden. We'll have a group photo and then we can enjoy the lunch.
We are because earlier it used to be through. Just an announcement, we will reconvene at 1:30 when there will be a panel discussion.
where I so between weighted and unweighted weights and polynomial because it's interesting you can't do the usual trick of what like weight of 5 you can't replace like the sequence of 5. Yeah, small weight
Also, my student is advised by me. As I said, mentioned, he's in his 5th year, so next year he'll be looking for postdocs. So all of those who are hiring postdocs, please put your phones away and start listening. And yes, so yeah, over to you, Ramesh.
Thank you, Anand. And thanks for the advertisement. So I'll be talking about recovering planted subgraphs. So I start with the widely popular planted clique problem that many of you might have seen. So we take a random graph, Haddonfield random graph, where every edge is with probability p, and on a random set we complete the clique, or equivalently I'll use an independent set of size k, and then the goal is to recover this planted clique or an independent set. You could also ask a different goal, which is to say, okay, I'm happy with any independent set of size larger than k because you have planted one of size k, and for k greater than 2 log n, your planted thing will be the unique, with high probability, the unique independent set, maximum independent set. So these goals coincide. And what do we know about this problem? If k is smaller than 2 log n, there is not even enough information here to uniquely recover this set S. And that is from the information side. For computationally, we only know of algorithms when k becomes as large as square root n. So this leads to this famous statistical computational gap for this problem. And you could also consider an easier goal where you just an hypothesis testing variant where you say you just want to distinguish this model from a null model which is just an random graph, and we'll also talk a bit about that. So what do we know about algorithms for doing this? Well, if the problems become easy when k becomes larger, for example, if k is as large as close to n, then the independent set or clique really stands out, and even the degrees will tell you the answer. For example, k larger than square root n log n. And the state-of-the-art thing for this is that we can remove this log n factor, and even a simple spectral test which looks at the eigenvalues of this normalized adjacency, this signed adjacency matrix for p equals to r. This is the plus minus 1 signed adjacency matrix. For a random graph, we know the largest eigenvalue is at most square root n, while when we planted the signal, the indicator vector of the signal even gives this quadratic form k. So when k is larger than square root n, you can distinguish this, and this paper of Alan Krivellevich-Sudakov turned this into a recovery algorithm using the eigenvectors. And as I said, there's a big open problem whether we can improve on this. In fact, there are some lower bounds based upon like sum of squares, which show that that may not be possible. Then the next step in this line is to consider semi-random models where you allow some adversary to sort of get a more typical instance of the problem. I'll not go into that detail, I'll just talk about this very powerful model there, this influential paper of Feige and Killian, which introduces this model where they say that now you are allowed to modify the graph and you can allow an arbitrary subgraph on V minus S to sit. And even in this notion, the notion of recovery changes. And what are the appropriate notion of recovery is, we can do something very interesting in this very recent line of work. I'll not go into these details. And so this broadly falls under this template of beyond worst case algorithm design. Usually I'll spend a couple of minutes on this, but for today I'll ask you to believe Tim and Feige on this. And I'll instead go to the problem that we consider, which is what other planted structure can we recover in this sort of a model. So let me describe our model, which is that you have a set S of size k, where you plant some combinatorial structure, like this is a pre-specified combinatorial structure, gamma. And you have this could be an arbitrary structure gamma which satisfies this, this could be an arbitrary subgraph which satisfies this structural combinatorial structure property gamma. And the rest of the edges are random. For example, just to make it concrete, you could plant R independent sets, R coloring on the set of vertices S, and you could ask whether you can recover this planted structure, planted R coloring. So this is the random model, and we also consider a semi-random model where we allow some adversary. And the model we consider is actually this complementary to this Feige-Killian model, where we say, okay, the edges in the cut can be arbitrary, they can be anything, and we allow some other adversaries as well, which I'll not go into, but yeah, we can allow some semi-randomness here as well. And so what is known about this? Have people studied this? So people have studied these sort of things for densest k subgraph problems. But for this particular problem of R coloring, there was this paper of Pravesh, Santosh, Alex and Jeff, which gave a lower bound of R square root n for recovery. So this was using this planted clique hypothesis, which itself says that the planted clique cannot be done better than square root n. And for R equals to 2, there were some results. But the result I'm going to tell you about today is the general result. The result we have this for general R coloring. This is jointly with Anand and Prasad, where we show that you can almost match this lower bound. You can recover a set T which has a large overlap with the planted set. And this is using SDPs, which is also the kind of the standard thing to get robustness here, is using SDPs and sum of squares. So the idea is that you may, so one idea may be, okay, you want to get the edges of this color class, you want to focus on the edges of the color class, not the arbitrary edges. So that runs into some issues. But the right thing to do is you can try to recover all these independent sets. So one thing is, of course, you could try to peel it, and in some black box we use independent set algorithms. That also runs into some issues which I'll not be able to talk about in this talk, but I can say that SDP can do that stuff. SDP can try to recover all those independent sets parallelly, simultaneously. And this is our relaxation, so this is for R equals to 2 for simplicity, but everything works out for general R as well. So let me tell you this SDP through this intended solution. So what is the intent of this SDP? For all the vertices in V minus S, which are not the part of this planted thing, we want to set it to the 0 vector. And for the vertices which are in the color class, we want to maybe cluster it like we have done it here in this pink vector. We want to cluster one color class here, and the second color class we want to cluster it away from it. So we want to cluster color classes away from each other, and then somehow we ask a vertex to choose which color class does it want to be part of. And I'll not go into this analysis. I'll just say it goes through a very nice connection to the Lowas theta SDP, and we can show that this works. And the next thing is you would ask, okay, if it works for graphs, can it work for hypergraphs? And actually, this machinery going from r equals to 1 to general value of r does work after you add appropriate levels of SOS. So this is for an L uniform hypergraph. So that at this point the problem becomes about planted, clique, or independent set in a hypergraph. And what do we know there? It's about certifying bounds on a semi-random hypergraph. So there are some results, but they do not have the right dependence either in the terms of n or p. They seem to be away. And also these are not SOS bounds. These are not robust certificates. These are only in the random graph. In the SOS certificates, which will be robust to these adversaries, they're only known for n to the power 3 by 4. This is the paper by Alan O'Donnell Whitmer, which studies more general CSPs, but they also talk about independent sets. And in an upcoming work with Pravesh, Anand, and Prasad, we improve on this. We show that we can get the correct dependence on n and an improved dependence on p. And also we designed robust certificates which will handle these semi-random adversaries. And I'll just mention a few ideas that we use. The technical novelty is in the odd arity case where the standard flattening doesn't work, and we have to do some tensor-based analysis, which goes to some analyzing eigenvalues of random chaos matrices arising out of these hypergraphs. And for these, there are already existing results which are suboptimal, but then we can use this recent progress on matrix concentration to improve those results and get log-free dependence. So that is about the snapshot of my work in this area. I did not talk about this Feige-Killian model, and for semi-random hypergraph there also we have some results. I'll let this stay for like 5 seconds or so. And I'll just end with one open direction, which is that in this work we looked at R coloring. But in general, you could ask this question that I could plant any subgraph, arbitrary subgraph, which is somehow not present in a random graph. And you should be able to tell the two apart, like distinguish and recover this. So already there is some actually work. There is a theory of how to like detect this, like detect this model from a model which does not have like a random graph model. You can detect these two apart. But a more general theory of recovery remains elusive, and that is, I think, a very interesting direction. And I think I'll end with that.
We have time for a few quick questions while the next speaker sets up.
So does your result extend the Alan O'Donnell Whitmer stuff? Is it in SOS based?
Right. So their result is actually tied for this what they prove, which is about CSPs. But they also study this. They have this random matrix bounds, which are actually handle much general class of polynomials. If you try to use that directly to R polynomial, which is maximum summation over I in Vxi, the independent set polynomial, that bound is actually suboptimal there. For that particular polynomial, we can prove better bounds using all this stuff.
Okay, let's thank Ramesh again. So the next speaker is Aditya. So he's also a final year student. He's also graduating soon, looking for postdoc positions. So if you missed out on what was happening in the previous talk, there's still more chance to hire the next one.
Where is the full thingy? Is this folder? No,
Control L.
So I think the panel earlier established very well that connectivity is the future of graph algorithms. I work on the future, so if you want to work on the future, hire me.
The mic.
Right. Am I audible all the way at the back? Yeah, right. So the problem, I'm going to talk about my work that's on the online connectivity augmentation problem. This is joint work with Mohit Garg, who is also here in the audience. I saw him come in. And yeah, it's going to appear in SODA 26. Right, so what is the problem? I'm going to give you a graph, and I'm also going to give you an extra set of links, candidate edges that I call links. What I tell you upfront is that this graph I give you is k edge connected, that if you pick any two vertices in the graph, there's going to be k edge disjoint paths between them. And what I want you to do is to buy a minimal subset of these links that are available to you to make the graph go from k edge connectivity to being k plus 1 edge connected. And so we abbreviate it as CAP, C-A-P, connectivity augmentation problem. And I'm also defining general XAP here, where you can substitute X with anything. You can have a path augmentation, tree augmentation, cycle augmentation. I might use some of those terms later, so I'm just defining that. You can have a PAB, a tab, and so on and so forth. So that is just connectivity augmentation. I said I work on online connectivity augmentation. What does that mean? So the last couple of days we have talked a lot about the dynamic model, where there's some uncertainty about the input. So this is somewhat similar, but the difficulty is a little different. There we are trying to optimize the runtime while keeping a good approximation ratio. In online, in some sense, I'm giving you as much runtime as you want, but I limit your power in that once you make a choice, you cannot renege on it. So every decision is irrevocable. So that is, in our case, if you buy a link, you cannot drop it later. And what you're going to optimize is something very similar to our usual approximation ratio. Here we call it completive ratio, and that's the ratio of the cost incurred by your online algorithm to the offline out. So specifically for online CAP, what this means is that the graph and links are given to you upfront, but the connectivity request, I don't want you to connect the entire graph to go to k plus 1, rather ST pairs arrive online, and for every such request pair, I want you to ensure that there are k edge disjoint paths between them. So that is what I mean by online CAP. So what did we know about this problem? So CAP is known to be APX hard. You cannot design a p-task for it. A two approximation has been long known. This is just one. I think multiple were known. And there has been a long line of works that has tried to get better than two approximations. The current best, I think, is 1.393 for the unweighted case, and so for the unweighted case, and for the weighted case it's 1.5 plus epsilon. So that's the offline case. What do we know for online? So in one of Anupam's earlier papers, it's for a more general problem, in that the request is not just SITI, it also comes with a R. And what that R means is that in my case, I'm asking you to go from k to k plus 1. In the survivable network design problem, that's what they solve. You have to ensure that there are edge disjoint paths between every pair, and every request comes with this R. But they solve a more general case, but what that means for CAP is that you get a k log cube n algorithm. And this is the only thing that is known for the general setting. For online connectivity augmentation, the specific case of tree augmentation has been studied, and there we have a tight log n completive ratio. Alright, so what do? We bring the upper bound for general CAP from that k log cube n to log square n for the weighted case, and for the unweighted case, we bring it further down to log n. Note that in both cases, we get rid of that k factor that is also there. And we also generalize the known lower bound, in that earlier it was just known for the online case. Here, what we say that even if you weaken the adversary a little bit, in that the adversary can decide what request to send you, but they cannot decide the order in which they appear. Even in that case, the log n lower bound still holds. And finally, we also give some simpler algorithms for TAP. So what I'm going to do is I'm going to give a very broad outline of this log n completive unweighted CAP algorithm that we have. So the first step is to get rid of that k factor that we had. And how do I do that? So there is this old structural graph theory result by Dinitz, Karzanov and Lomonosov from the 70s, which says that if I give you a graph, what you can do is you can construct another graph from this that in some sense maintains all the min cuts in the graph. What it also says that this new graph that we construct is going to be what is called a cactus. What is a cactus? It's a graph in which every edge is part of exactly one cycle. That is, it's exactly a two-edge connected graph. And again, like I said, XAP, where you can substitute X with the CAC, that's a cactus. So, and what this allows me to say is that if you can get an alpha competitive online algorithm for cactus augmentation, you can get an alpha commutative online algorithm for connectivity augmentation. So I'm going to solve cactus instead of connectivity augmentation, and by getting rid of the k there, from the k connected graph, I brought it down to a two connected graph. That is how we get rid of the k. This is what a cactus looks like. If you can see, any edge in the graph is part of exactly one cycle, one local cycle, and each cycle, these individual cycles cannot altogether form a big loop, because then an edge would be part of its local cycle and then a global cycle. So you can think of a cactus in some sense as a tree of cycles, and this is what we exploit. So I assign any arbitrary vertex in the graph as my root, and I sort of look at these two structures that are inbuilt in the graph that is given to me. There is this underlying tree and there are these individual cycles. Now, for tree augmentation, we already had a log-n commutative algorithm. For cycle augmentation, what we do is that we reduce the problem through node weighted Steiner forest and then use edge weighted Steiner forest to approximate it. So, using that, we essentially can reduce it to Steiner forest and get a log-n commutative algorithm for cycle augmentation also. And in what we do for getting a better algorithm for cactus is that we sort of put them together. So every time a request arrives, my algorithm will decide whether to send it. Okay, and then I will construct a lot of individual instances. For every cycle, I'm going to construct a cycle augmentation instance, and so some links go there. And I'm also going to construct a tree augmentation instance on this underlying tree that we form. And I'm not explaining how the links get sent to each instance. When a request arrives, my algorithm decides whether to send it to a local cycle or to send it to the tree instance. And we do a smart charging argument to ensure that the compute ratio essentially doesn't blow up too much. This is a very, very high level idea of what happens, but this is the underlying intuition for the algorithm. And yeah, I think my 8 minutes are up. So yeah, that's
Time for a few quick questions.
So does your algorithm have implications for online SMBP?
No, not yet. I would like to generalize things further, but at this point, nothing for online SND.
Are the lower bounds based on some LP?
No. Commutative lower bound. I can explain that also in under 5 minutes if you want to talk later.
Okay, let's thank Aditya again. So next is Debajyoti. He's not graduating. He's not graduating, so you don't have to stay awake. But he has proved enough theorems to graduate if he wants to. I guess he wants to stay back and prove more theorems. So today he'll tell us about one of those things.
Okay, so a disclaimer first. So this is what I'm going to talk about is going to be more of a puzzle problem than a problem on graphs. Okay, so suppose you are given a square of side length k and say k is an integer for simplicity, and you are given a collection of n rectangles and the dimensions of these rectangles are integers between 1 and k. And now you want to pack as many rectangles as possible into this square. Okay. Okay, and such that no two of these rectangles overlap each other. Now for every rectangle, we are only going to restrict to axis aligned packings. That is, for example, consider this orange rectangle here. There are only two ways in which you can pack them. Either you pack it vertically in this fashion, or you can rotate it by 90 degrees and pack it in this way. And now subject to this, you want to pack as many rectangles as you can into this square. So for example, for this instance that I have here, this shows a packing of 6 of these rectangles. Okay, I hope the problem is clear. It's a very simple to state problem. And now as you can imagine, this has wide applications in practice ranging from loading items onto trucks, robotics, VLSI, etc. So what's known in theory? So first of all, the problem was shown to be strongly NP hard even when all rectangles are squares. And therefore, we look for approximation algorithms. So an alpha approximation is an algorithm that can pack at least 1 by alpha fraction of the optimal number of rectangles for any input instance. Okay, so let's look at what was known before. So more than 20 years ago, Janssen and Zhang gave a 2 plus epsilon approximation for this problem. And then in 2017, there was a paper by Arindam and others where they improved this to a 4 by 3 plus epsilon approximation. And this, prior to our work, this was the best known approximation ratio for the problem achievable in polynomial time. However, if we make certain more assumptions about the input, then it is possible to get better approximation ratios. So for example, there is a q-pitas known if you assume that the side length of the square is quasi-polynomially bounded in the number of input rectangles. That is, you can get a 1 plus epsilon approximation in quasi-polynomial time. And then again in 2021, Arindam and others showed that in pseudo-polynomial time, you can get a 5 by 4 plus epsilon approximation. That is, in other words, if you assume the side length of the square to be polynomially bounded, then this 4 by 3 approximation improves to 5 by 4. And for the special case when all rectangles are squares, there is a pitas known. Okay, and there are some other results known as well in the parameterized approximation setting. But after all this, the big open question that remains is, does there exist a pitas for the problem, for the general rectangle packing question? And in 2017, there was a survey, again by Arindam and others, where they made a list of the top 10 open problems in geometric packing, and obtaining a pitas for this rectangle knapsack question was listed as one of these problems. Okay, so a lot of advertisement. Finally, in our work, we show that there indeed is a pitas for the problem. Okay, so I'll briefly talk about the techniques that we use in our work. Okay, so all the previous works, they rely on a common template. That is, we start with the optimal packing of the rectangles and then somehow try to convert it to a packing with some nice structure. And the hope is that if you can show and maybe in the process we can delete a small fraction of rectangles. And the hope is that if you can show the existence of these structured solutions, then there are some dynamic programming techniques by which you can actually compute the best structured solution. Okay, so let's begin with the classification of these rectangles. So here delta is some constant depending on epsilon. So we call a rectangle to be large if both of its dimensions exceed delta k. Then we call it small if both of its sides are at most delta k. And then among the remaining rectangles, if the width of a rectangle is more than delta k, we call them horizontal, and the remaining ones are called vertical rectangles. Okay, so let's begin with the large rectangles. So notice that since the area of each large rectangle is at least a delta square fraction of the area of the knapsack, area of the square, there can only be a constant number of such large rectangles in any feasible packing, right? And therefore, if we assume that the size of the optimal packing is large enough, then the number of these large rectangles is only going to be an epsilon fraction of opt. And therefore, we can simply discard them, because in the other case when opt is small, we can just do a brute force enumeration. Next, if we consider the small rectangles, unlike the large ones, in principle there can be arbitrarily many of these small rectangles, but intuitively you can imagine them to be like sand particles spread in the packing. And indeed it turns out that there are some greedy ways by which you can repack these items later. So these are not the problematic ones. So we are left with just the horizontal and vertical rectangles. And indeed it turns out that all the core of the hardness of these rectangle packing problems is captured by these skewed rectangles. And the reason behind this is that the interaction, like these rectangles can interact in very complicated ways near the boundary. So for example, this boundary curve between the horizontal and vertical rectangles, it can have a very large complexity, and it's not even possible to approximate this curve because these rectangles can tightly fit into each other. So what previous works have done in order to handle this is to consider structured packings which are called container packings. So a container packing is a packing where the knapsack is partitioned into a constant number of containers. So we have horizontal containers and vertical containers, and in horizontal containers, a subset of horizontal items are just stacked one above the other, And similarly, inside a vertical container, a set of vertical items will be stacked one beside the other. And the container packing is one where the whole knapsack is partitioned into a constant number of these containers. So the advantage of doing this is that now these interactions between these horizontal and vertical items are now completely absent here. And intuitively, we have transformed this two-dimensional packing problem into a constant number of 1D knapsack problems. And in fact, there is a result which says that there is a p-task to compute the best such container packing. And by best, I mean the one that packs the maximum number of rectangles. So as long as the number of containers is a constant, there is a p-task to find the best container packing. And this is done via reduction to the generalized assignment problem. But let's not worry about that. So once we have such a result, our task now boils down to a completely structural question. And that is, how many rectangles can we guarantee that the best container packing contains? So formally, if we let opt container be the best container packing, that is the container packing that packs the maximum number of rectangles, and opt be the optimal packing, then clearly this opt container is a lower bound on opt, because any container packing is also a feasible packing. So the question that we ask is, what is the smallest alpha such that we can guarantee that the best container packing will always pack at least a 1 by alpha fraction of the optimal number of rectangles. And this alpha is going to be the approximation ratio of our algorithm, courtesy of previous lemma. Right? So the previous works have tried to show some upper bounds on alpha. For example, the initial paper by Janssen and Zhang had showed an upper bound of 2 plus epsilon for alpha, and then Arindam and others had improved this upper bound to 4 by 3 plus epsilon. And in our work, finally we show that this alpha is in fact at most 1 plus epsilon. And this is how we obtain a p-task. So I'll just briefly have one slide to say how we get this improved upper bound on alpha. So we start with the optimal packing of the horizontal and vertical rectangles, and then we apply something called the corridor decomposition framework. And this is one of the very beautiful results in the area of rectangle packing, which intuitively says that it is always possible to partition the knapsack, partition this whole square into a constant number of rectilinear polygons by deleting just a small fraction of rectangles. And once we have this, we show a new resource contraction lemma, and then using that we do some corridor processing in order to convert these rectilinear polygons into containers. But this is a very high level sketch of something that took around 10 to 15 pages to write, but I don't have time to go into that. So summarizing, we provide a p-task for this rectangle knapsack question, and the only bad thing about our algorithm is that the running time is super high. It's n to the power some function of epsilon. However, it turns out that if you assume the k-sum conjecture to be true, which is one of the fundamental conjectures in fine-grained complexity, then we establish that any p-task must take n to the power omega 1 by epsilon time. So in fact, there is not much hope to get fast algorithms for knapsack. And now for the general case when rectangles might have weights, that is, now now rectangles have weights and we want to pack a maximum weight subset of rectangles into the knapsack. For this, unfortunately, it turns out that container packings don't work. I mean, we cannot get p-tasks just by using container packings. So we show the existence of instances where the best container packing can pack only 2/3 of the optimal weight of rectangles. However, we then go beyond container packings to more general solutions, and we are able to get slightly improved approximation ratios of roughly 1.497. So yeah, that's all. Thank you.
We have time for a few quick questions.
So can you give some intuition? You had shown that L-shaped thing with a very
Yeah.
squiggly line out there.
Yes.
How did that get converted into a container?
Yes. So I have a few slides after this. Okay, so what was actually known before? So yeah, these interactions we cannot get rid of them completely. But okay, but here we are allowed to rotate the rectangles. So imagine that all the other rectangles, if they were absent, then you could have rotated these vertical rectangles above these horizontal rectangles and got a single container. But it's not clear how to do this always. So what was known before was that by deleting some small fraction of rectangles, it's possible to convert these into containers, and the remaining rectangles, all of them fit inside a very thin strip. And this can be intuitively seen, because if you just delete the rectangles which lie very close to the boundary, then those fit into the empty strip. Those fit into a very thin strip. But the main obstacle is how do we repack this strip into the container, and that is where our main contribution was. So intuitively we devised a new processing scheme where the number of containers that we get is actually much smaller, and using that we show that there should be sufficient number of large containers, and then we delete some random strips inside the large containers and push these containers towards the left and bottom, and in this way we show that we can repack this strip either at the top or the right boundary of the knapsack. So it's quite involved, but yeah. Okay. Thanks.
Okay, let's thank Debujyoti. Okay, our next speaker is KVN Srinivas. He's also being advised by Arindam. He's been also doing a lot of cool work on approximation algorithms.
Okay, so hello everyone. I'll be talking about the best fit algorithm for bin packing in the random order model, and this is joint work with Anish Heber and my advisor Arindam Khan. So just to recall the bin packing problem, we are given a set of items where each item has size in between 0 and 1, and the goal is to pack them into minimum number of unit capacity bins. And so bin packing is a very classical NP-hard problem, and it has been studied from an approximation perspective since 70s. So there are some very practical algorithms like next fit and best fit that achieve very good approximation ratios. And from a theoretical perspective, there are algorithms that obtain very close to optimal number of bins. So although they are polynomial time, they are like quite impractical because of the huge constants hidden. So we are interested in studying bin packing under the random order model. So here the input set is chosen by the adversary, but the arrival order is chosen uniformly randomly among all the n factorial permutations. And the goal is to pack all the items in online fashion, which means that we want to pack each arriving item without having the future knowledge of the arriving items. And it's a very well motivated model. For example, it's stronger than the IID model, and people study it for that reason. And to measure the performance of an algorithm, we do it as follows. If I is the input set and I sigma is some uniform random permutation of I, which comes to us as the input sequence, then the random order ratio of alg is defined as follows. So we look at all the input instances I for which opt I is large. So we are interested in the asymptotics, and we are interested in the maximum ratio maximum of this ratio, which is the expected cost of the algorithm by the optimal cost. Okay, so a pretty natural definition. So we are interested in studying best fit under this random order model. So what is the best fit algorithm? So whenever an item arrives, we pack that arrived item into the fullest bin that it can fit into. If there is no bin that it can fit into, we open a new bin. Okay, so for example, consider this instance. So the first three items are packed like this. Now the green item comes, which can fit into these two bins, but we pack it in the first bin because that's the fullest bin among these two. And 0.5 and then 0.4 comes again. We pack it in the second bin, even though it fits in the second and third bins because that's the fullest. Okay, so again, like best fit has been studied very well since 70s, and we now know that it achieves an approximation ratio of 1.7. And that is tight, and it's very well motivated to study this algorithm because it's one of the very practical algorithms for bin packing. Okay, so we are interested in studying best fit under random order. So this was first studied by Kenyon in 1996, who showed that the random order ratio of best fit lies in between 1.08 and 1.5, and she also conjectured that it lies somewhere around 1.15. And so, yeah, there has been only progress in some special cases to break this. Yeah, okay. So there has only been improvements in special cases, but in the general case, we don't know whether 1.5 is the correct ratio or not. So until our work where we show that this is not the correct ratio, and we break this barrier of 1.5 by showing that the random order ratio of best fit is at most 1.5 minus 10 power minus 10, some very small epsilon. We also make some progress on the lower bound front, but in this talk I would like to highlight two techniques that we use for the upper bound. So the first technique is that of weight functions. So it has been used in like multiple bin packing works in the past as well. So for our purposes, for now, let's assume that all items have size greater than 1 by 4. And let's categorize items into three types. If the size is in between 1 by 4 and 1 by 3, we call the item small. If it's in between 1 by 3 and 1 by 2, we call it medium. And if it's in between 1 by 2 and 1, we call it large. Okay? And we assign weights to items as follows. If the item is either small or medium, we assign a weight of 0.5. And if the item is large, we assign a weight of 1. So intuitively, weight functions, it get rid of all the complexities with the actual sizes of the items. So we lose some information, but this makes the analysis much easier. So let's see how these weight functions help us. So one can show that any bin in the optimal packing has a weight at most 1.5, because at most 3 items can fit in a bin, and a large item can fit with at most one medium or small item. That can be verified. And we can also show that any bin in best fit has weight at least 1, because best fit will pack at least 2 items in each bin with some very rare exceptions. So this immediately gives us that best fit has an approximation ratio of at most 1.5 in the special case when all the items have size greater than 1 by 4. Okay, but now we want to harness the power of random order and show that we can achieve a ratio strictly better than 1.5. Okay, so how do we do that? So note that in this claim, if we can show that there are a lot of bins in best fit that have weight not just at least 1 but at least 1.5, then we beat this 1.5 strictly. Okay, so that's our revised goal. So we want to show that best fit packs a lot of bins of weight 1.5 due to random order. This gets us to the second technique, which is the technique of gadgets. So what random order in general, for like any random order problem, like it ensures that there are a lot of favorable patterns, or what we call gadgets, in our work. So for our example, one gadget is what is called S triplet. This is nothing but a set of 3 consecutive small items in the input sequence. And we want to claim that an S triplet will create a bin of weight at least 3 by 2. So for example, consider an instance and S arbitrary point in time, and suppose this is the packing till then, and S1, S2, S3 is an S triplet that's about to come. So if one of S1, S2, S3 is packed in one of these bins, okay, so first note that each of these 3 bins have a weight at least 1, because large items have weight 1 and medium and small items have weight half. So if one of these 3 items is packed in one of these bins, then that creates a bin of weight 3 by 2. Otherwise, note that every small item has size at most 1 by 3. So they all will be packed in one bin, and this will create a new bin of weight 3 by 2. So in this way, every S triplet will create bin of weight 3 by 2. And yeah, so one question would be like, what if there are not small items at all? So in that case, like we can come up with some other gadgets, and those gadgets will create bins of weight 3 by 2. But this is a very high level overview of the technique. Yeah, so to conclude, we show that the upper bound on the random order ratio of best fit is like strictly less than 1.5. And okay, so it's important to know that so the lower bound has been improved. So Kenyon gave a lower bound of 1.08, but it has been improved recently by Epstein and Levin to 1.16, and the conjecture ratio was 1.15 around. So maybe there is not much on the lower bound front to be done. So on the upper bound front, there are quite a few interesting open problems. For example, like can we beat 1.5 comprehensively for the IID model, which is a weaker model than the random order model? And can we beat 1.5 comprehensively for like even special cases like 1/4 to 1/2? So these are known to be some important special cases of bin packing for some other reasons. These are called 3 partition instances. Yeah, so that ends. Yeah, thank you.
Okay, so time for maybe a quick question.
So, Kavian, can you comment on why you're gaining so little? It's like this clean idea seems to suggest you should lose big.
Okay, so the number of gadgets seem to be very little. So we also have to show that the number of gadgets is constant fraction, and that constant fraction, yeah, it turns out to be very little.
Okay, let's thank Kemian again. So next is Nirjar. He's a MTech research student here. MTech research student here. Second year?
Second year, yeah.
Okay, so
Applying
graduate.
for grad school.
Applying for grad school, okay. So those of you who are looking for PhD students, please listen up. Yeah, he's working with Siddharth and he'll be talking about his work on similarity diversity search.
Am I audible? Hello?
Yes.
Okay, yeah, thank you. So this is work with Siddharth, Shivam who is a postdoc, and Kiran who is at Microsoft Research. So this work actually came out of a talk that Kiran gave here about diverse similarity search, actually about approximate nearest neighbor search, which companies like Microsoft and Google are using a lot. And the problem kind of came out very nicely out of a discussion that we had, and right now the solution that we will discuss in this talk is actually being kind of in pipeline to be deployed within Microsoft. So nearest neighbor search is a very common problem occurring in many large-scale industrial applications. For example, in recommender systems, search engines, and advertisements. What is the problem? You have a large collection of items, and there's a query that comes in. You have to return a small set of items that are relevant to the query, and I'll define what relevant means. But the main challenge here is to kind of retrieve this small set of items very fast, because this large collection is actually very large, like in scales of billions. So the formal setup is as follows, that you have a set of vectors P in RD. D is moderately large, and the size of P is n. Here n is very large. You have given an integer k, which is the number of items or vectors that you have to retrieve. You also are given a similarity function that compares to, takes into vectors and tells you how similar they are to each other. And this kind of captures the relevance aspect that I mentioned previously. You are also given an approximation factor alpha. And what we want is kind of to build a data structure and an algorithm that, given any query in this RD, quickly returns a set S of size k from this set P, such that the similarity of the ith most similar vector in this set S is at least alpha times the similarity of the ith most similar vector in all of P. So you are kind of preserving similarity within a factor of alpha. And what alpha equals to 1 actually kind of requires linear time, but there are several solutions known for alpha less than 1. So if you allow for approximation, you can actually get very fast algorithms of sublinear time. This has been studied for a long time, like starting with locality sensitive hashing. There are recent graph-based methods as well. But what we wanted to, what we did in this work is a bit complementary to this work, which is kind of study this problem of diversity in nearest neighbor search. And this is a problem that actually came out within Microsoft's policy, and even other companies are kind of looking at this problem. So the problem is as follows. Think of an ad example, right? As a Microsoft or Google, they have a huge collection of ads where there are a few big sellers who have placed a lot of ads, and there are many small sellers who have placed few number of ads. But when a user types in a query like men's running shoes, what Google ends up showing is a bunch of ads from the dominant sellers who have placed a lot of ads. These are big players. But what we want to do, or like Google or Microsoft wants to do, is kind of improve diversity in the search results that they return. Similarly, for retrieval augmented generation, this is another application of approximate nearest neighbor search that is coming up in a lot of like recent LLM scenarios, where you want to retrieve a set of documents given a query and feed those documents into an LLM to generate a nice response. So the more diverse the set of documents is, the more informed the response will be. Similarly for recommendations. So having this motivation, let me quickly set up the problem. So we have the vector v, every vector v in P, right? P was the set of vectors that we had, is associated with attributes denoted by ATB of V, which is a subset in this set 1 to C. So you can think of them as sellers or colors of products or brands or price range. So this 1 to C captures a lot of this kind of attributes you can assign to a product or an advertisement, and that is given by this set ATB of V for a particular vector V. Let Di denote the set of all vectors that have this attribute I. And then what previous work was trying to do is trying to restrict the number of vectors that you are allowed to pick in S from this particular set Di, right? So you want to kind of put a hard constraint of K prime on the number of items you allow from this particular attribute. But the question is how to choose this K prime. It's not clear a priori what's a good K prime is or what sort of guarantees you can get by choosing different K primes. And in practice, you can actually see that this is an experiment we did on Amazon dataset. We ran a query called shirts. What the standard retrieval algorithm retrieved was that the majority color was overrepresented in the solution. When you put this K prime constraint, okay, you can get a diverse solution. But what happens when the query is blue shirt, right? Here, the standard algorithm actually returns a lot of blue colored shirts. But if you put the constraint K prime, then you are actually cutting down all the nice solutions that you would get otherwise without this hard constraint. So kind of to bridge this gap between relevance and diversity, we kind of looked at the problem from a different perspective, taking inspiration from welfare economics. So we looked at these attributes as agents participating in the process, and these agents derive utilities from the set that we return. And the utility is defined as the cumulative similarity to the query for every vector that belongs to the set S that you return, and also in the set Di, which is the set that has this attribute I, right? So every vector V that has attribute I contributes to the utility of the ith agent. And then with this perspective, you can actually show that the standard ANN problem is equivalent to solving this problem. And what is this problem? This is nothing but a social welfare maximization problem. This is the arithmetic mean of utilities of the agents. It's well studied in welfare economics. But what we figured out is that, okay, to incorporate diversity, we can actually look at the Nash social welfare, which is the geometric mean of utilities of the agents. And it has very nice axiomatic properties. Here are a list of axiomatic properties that I'll not go into, but I can talk offline. And the nice thing is that it balances relevance and diversity smoothly. So we did some experiments as well, and here's the same example of the shirts query. Nash is able to capture diversity when the query is a general query. But when we go to the blue shirt query, the specific query, here Nash is able to capture a lot of relevant queries, like it returns a lot of blue shirts actually. So on real world data sets as well, this seems to work. And here are some theoretical results. It's basically we give algorithms that can solve the optimization problem exactly when every vector is associated with exactly one attribute. When they are associated with multiple attributes, it becomes NP hard, and we give an approximation algorithm for that as well. But the nice thing again is that we actually, our formulation extends to this generalized P-mean welfare, where by changing this quantity P, you can actually interpolate between the standard approximate nearest neighbor search, the Nash nearest neighbor search, and the complete diverse solution, which is like k prime equals 1, the constraint equals 1. So these are some results on data sets that we ran, and in practice we actually see on large scale data sets this algorithm kind of performs very nicely. Here is the solution that our formulation picks. This is the completely constraint solution, and this is the standard.
This is a theory talk, so we don't want to expand.
Yeah. No, but I think going back to Barna's point that we algorithm people should advertise to practical people. So
we also don't care about applications.
Yeah. Okay, so these are some results we had. And in conclusion, like there are some open problems, but okay, I'll be happy to talk about them.
Okay, any questions on the theoretical part of the talk?
Yeah, go ahead.
How do you choose eta?
Sorry?
How do you choose the parameter eta?
Eta is just a small constant. It's just there to kind of avoid the degenerate solution of being 0, right? If you have like very few attributes, you want to retrieve a small set, but you have a large set of attributes, then you can.
Is there a principal way to choose it, or you choose something?
I mean, so you can choose it like something like the minimum pairwise distance in their data set, that suffices. But yeah, in general, it doesn't really affect the solution that much. We tried out many values, but yeah, it's robust to that setting. There's another question. Do we have time?
Okay, yeah, maybe the question.
Arbitrary similarity function, what properties are you assuming about the similarity?
So we don't assume, so our formulation does not assume any arbitrary similarity function. Where we need properties of the similarity function is if you want fast retrieval algorithms, which is what we build on in this in our algorithmic framework. So there something like inverse of the similarity, 1 by the similarity function, if it has like triangle inequality properties, then you will get very fast algorithms.
Okay, let's thank Nirjar again. Next talk is by Nikhilesh. He's a PhD student, advised by Rahul. Second year student? Third year student. So he'll be talking about his recent work on sublinear set cover.
Okay, I think I'm audible. Okay, hello everyone. So this talk is based on some of our recent work on sublinear set cover using membership queries. So this is joint work with our Professor Siddharth and Rahul. So let's just get right into it. So again, just a quick recap. We're working under the standard set cover setting. We have a ground set of n elements and a family f of m subsets. And the standard set cover problem is find the smallest collection of f subsets in f that cover our ground set. Now, in this work, we're going to look at this problem under the setting where we actually don't know all of the element set memberships a priori. So this kind of setting arises a lot where, for example, if finding these element set memberships is something that's an expensive task in itself. Like, for example, as a toy example, suppose we have a bunch of jobs and a bunch of machines, and we want to find the smallest collection of the jobs, the machines that can run all of the jobs. But suppose we don't know upfront which of the machines can run which jobs, then we'd have to run some expensive testing to find out whether a job and machine pair are compatible. So this is the kind of setting that we're interested in. Now, a very natural way to model this is in the membership query model. So in this model, what we have is a membership oracle. So essentially, the way to think of a membership oracle is like it's an oracle which takes as input an element ei and a set sj, and the oracle answers whether that element is in the set or not. And suppose we have this oracle access, but we don't know anything else about our set instance. Now the question that we are trying to answer is, can we find a good set cover using a small number of membership queries? And here by good, I mean like a good approximation factor. Okay, so let's try to see what we can do. A very trivial approach. You just use, you have m subsets and n elements. You just run all possible pairwise membership queries, and that way you retrieve the entire set cover instance. And then you can just run your favorite set cover algorithm to find the thing. So you can do it with mn queries. But the interesting question is, can we do better than that? Unfortunately, it turns out the answer is no, right at the beginning. So in fact, there's some work by Indic and collaborators in SODA 2018, and they showed that even to distinguish between instances where opt is 2 and opt is large, like opt is m, requires something like omega mn membership queries. So it seems like right on the onset we're doomed. But I'll promise you we can still say something interesting about this problem. In particular, what we do in our work is that instead of just looking at this in the worst case regime, we take a more fine-grained and nuanced view of this and say that if we parameterize by the size of the optimal set cover, the claim is that we can actually say something interesting. And in particular, on instances where opt is small, the claim is that we can actually do much better than mn queries. So yeah, here are our kind of main results, just written down to two theorems here. So we have an upper bound and a matching lower bound. Just roughly paraphrasing what these say, what the upper bound and lower bound both say, is that at least for set cover instances where opt is, let's say, polynomially bounded away from m by some polylog factor, so opt is not too large, sufficiently far away, we can achieve a query complexity of m plus n times opt membership queries. So just to get a handle of this, if we look at m plus n times opt, when opt is something really large like m and n, this basically just degenerates to the old mn query complexity. But here what we're saying is that when opt is small, so for example when opt is constant, this is saying that we can actually do much better. We can in fact achieve something like order of m plus n queries, which is just linear in our parameter. So I mean, is linear in m and n rather. So it's much better than the mn guarantee we get. And we also have a matching lower bound, roughly speaking, that says that we can't do better than this, at least when opt is not too large. So okay, so instead of going over the algorithm in detail, since there are a lot of moving parts, what I'll do instead is kind of focus on one of the key ideas behind our algorithm, which I think will probably be interesting to a lot of people here. In particular, what I'll do is talk about this one particular sub-problem that we solve in the course of solving this algorithm, and that introduces some like nice theoretical and algorithmic ideas. So in particular, let's consider this simpler problem, right? So we were looking at set cover, but now instead let's look at this simpler problem of which I'll call finding a heavy needle in a haystack problem. So the problem is as follows. Again, we have the same set cover instance and we have a membership oracle. Now the goal is, instead of finding a set cover, our goal is just to find one single heavy set. And what do we mean by heavy set? It's a set that contains something like omega of n by opt elements, where opt is the size of the optimal set cover. Now if you're familiar with like the greedy algorithm for set cover, it should be clear why we're trying to do this, because if you can kind of run this if you have a query efficient algorithm to do this, we run it repeatedly, then we get a log n approximation for set cover. And note that it's not too hard to show that there'll always be at least one heavy set. So okay, this is the problem we're trying to solve. So how do we go about doing this? And here is kind of a very simple sort of folklore approach that maybe a lot of you might have seen at some point yourself. What we can do is just something, a simple kind of sketching approach. So we pick a small subsample of something like opt log m elements, and we query all of our sets with these opt log m elements. And then if we find a set which covers more than 1 by opt fraction in the sample, then we can, using some Chernoff style arguments, we can say that it's likely heavy in the entire population as well. So in particular, this approach will use the number of membership queries this uses is m opt log m, since opt log m per set, and we have m sets in total, and we find a heavy set with high probability this way. Now here's the question, can we beat this? This is sort of like maybe the standard Chernoff approach that a lot of us might have seen. But can we do better than this? In particular, can we remove this logarithmic term and find a heavy set using only m opt queries in expectation? And my claim is that yes, we can actually achieve this. And the key idea behind doing this is this idea of treating heavy and light sets in an asymmetric manner. So the idea is that we're really trying to find a needle in a haystack. So if we can somehow, let's say, use few queries on the light sets and many queries on all the at the cost of using maybe a large number of queries on the heavy sets, we're still fine, because we're really only trying to find that one heavy set. But the problem is, this is easier said than done, because we don't know, when a set comes to us, we don't know a priori whether it's heavy or not. So we don't really know how many queries we ought to use in it. But my claim is that we can still do it using a clever random walk based approach. I won't go into the details on this, but let me just roughly outline what we're trying to do. Essentially, suppose we have a set S that's given to us and we want to test whether it's heavy or light. What we'll do is something like the following. We'll simulate a random walk using that set. And the way we'll do it is, we'll start with a random walk in the origin, and then we'll sample an element uniformly at random from our ground set. And if that element is in the set, then a random walk moves to the right by some order of opt units. Otherwise, it moves to the left by 1 unit. So this essentially ensures that if our set is heavy, this random walk is going to drift towards the right, and if our set is light, it's going to drift towards the left. And we set up two different barriers. So one barrier at the right at something like 10 opt log m, and one barrier on the left at minus 10 opt. And if it crosses the right barrier, we report that set as heavy. If it crosses the left barrier, we say that the set is light. And the key idea here is that these two barriers are asymmetric. We have different barriers on the left and right, and that is really what helps us achieve our good performance. So what we can show, I won't go over the analysis. What we can show is that this tester algorithm actually achieves some kind of asymmetric properties like this. So if you just look at this table over here, we have the probability of error and the expected number of queries tabulated for light sets and heavy sets separately. And the main thing to notice is that these are different for light sets and heavy sets, as opposed to the earlier case where we were using the same number of queries and had the same error guarantees for both. In particular, notice that for light sets, we're only using order of opt queries for light sets instead of opt log n, while still achieving a low probability of error. So we're successful with high probability. And once you have this table, you can show it's not too hard to show that this algorithm, in fact, returns a heavy set with high probability and only uses mopt queries in expectation as opposed to mopt log n. Roughly because on each of the sets, light sets, there are m such light sets, and it uses only opt queries on them in expectation. And on heavy sets, it uses opt log m, but at most it queries them only a constant number of times before it finds one. So this gives us our mopt kind of query bound. So I'll stop here. There are a lot of other ideas that we use in the algorithm, but I mainly wanted to highlight this one thing because I think this idea of solving this kind of needle and haystack problem using asymmetry to solve this in an efficient manner is probably something that can see applications in other problems outside of set cover as well. So yeah, I'll wrap it up here for any questions. Thank you.
Do you have any questions? Yes.
I might have missed something, but
yeah.
In order to get your overall bound of n plus n times off,
yeah,
wouldn't you need to solve the heavy set problem in just m plus n queries instead of m?
Correct. You're absolutely right. And so yeah, this is really only the first step that goes into it. So the idea is that we have this problem of finding a heavy set in mopt queries, and then we can improve this further to m plus n, more or less exactly as you said, using some more ideas. And there one of the ideas we use is this kind of rejection sampling of an incidence. So instead of sampling a set uniformly at random, what we'll do is we'll instead try to sample an incidence uniformly at random from our set of incidences using some rejection sampling, and then run this algorithm on that sampled incidence. And then we can show that actually improves this by a further factor of opt. That's kind of the idea. And even that honestly will still only give us an mopt log n, and we still need some more clever ideas to actually bring that down all the way to mopt. Yeah, it's just a trailer.
Okay, any other quick questions? Okay, so let's thank all the speakers for the session. I think all of the student speakers, they are very keen to get your inputs on them, so they might approach you during the break. Please talk to them, share your valuable inputs and feedback with them. So we'll now break for tea. Since we are running a little behind schedule, we'll have a slightly shorter break. Let's meet back at 4 o'clock.
Tea was at 4, I guess. But Navin's talk was
Do we not have a break now?
now Navin's talk.
Okay, let's do that then.
No tea.
Sorry, no tea. There's one more talk now.
Can you email the slides? It's better if you use this.
Is it?
Yeah.
It's being live broadcast and these things. You can email to Akshay Nath and
I'll send you the So the login is
Almost all of us will get on the
Okay, so that's good legal side, but it's understood. Somebody to stop Okay, I'll check.
let people settle down. I think a lot of people stepped out. That's email address, right?
Yeah.
Oh yeah, test PowerPoint.
Has made several significant and foundational contributions to many areas in approximation algorithms, including network design, scheduling, routing, facility location, and many more. He's a fellow of the Indian Academy of Science and also a fellow of the Indian National Academy of Engineering. He's received numerous accolades for his contribution, including the prestigious Shanti Swarup Bhatnagar Award in the Mathematical Sciences category in 2016. Note that this is India's highest prize for excellence in science, mathematics, and technology. So join me in welcoming Professor Naveen and all yours.
Thank you, Ramesh. Thank you, the organizers. Thanks to the organizers for inviting me. I have not been doing a lot of graph algorithms. It's not on, yeah. Why is it not on?
Captain, does the mic with lapel
Okay. Okay. Can you hear me now? Yeah. So I must admit I've not been doing a lot of graph algorithms for the last few years. I only recently started working again with one of my students on a graph problem. And when we were doing that, we had to revisit some of the work I did with Nikhil, who is also in the audience, right, very last. This was 5 years ago. Yeah, these are 2 papers from 2020, right? The 20 is 2020, yeah. And so I'm going to talk about them today. Unfortunately, this was the COVID period, right? So I didn't get enough time, or we didn't have much occasion to talk about these results. So somehow they have remained hidden, and I thought this would also be a good opportunity for you to get to know about it. I also like this because somehow this connects the things that I like in graph algorithms, which is network design and cuts and flows. So all of it will come together here, and through planarity. So not a very difficult talk to follow, quite straightforward. And yeah, the last thing, there are enough experts in this audience who know this stuff way better than I do. So Anupam, Sanjeev, please cut me some slack. While the others, yeah, you should ask me questions, and I'm very happy to answer. Okay. So what is the setting we are in? So we have a graph G, and I'll call this a supply graph, and I'll usually draw it in black. And we have a demand graph H, which I'll always draw in red. And the vertex set of both the graphs are the same, the edge sets are different. We'll assume edge capacities are, every edge in the supply graph has a capacity, and it could be from the reals, but for this talk I'll assume they are primarily both the capacities and demands, but it could be anything. Right? The demands we'll assume again are integer, right? And in this talk we'll just assume they are 1. So this could be example supply and demand graph. And what's an integral routing of flow? So you want to find a path between the endpoints of every demand such that the paths through any edge do not exceed the capacity of that edge. Okay. So here would be these green arcs denote an integral routing of flow, right? So between this, this is the path I took, and between this is a demand, remember the red is a demand, so I took this. And of course I have not drawn a path for this, right? And that's because I cannot, right? There is no way of routing flow between the top vertex and the bottom vertex, because once I have, remember this is 1 unit of flow that is going along these green arcs, so I've taken up this 1 unit, this, and this, and now there is no path left from here to here. Right? So this, I cannot send 1 unit of flow. What's fractional routing? Well, I have to do the same thing. I have to send 1 unit of flow between the endpoints of every demand edge, but now I can send it fractionally. Right? So in this example, now the same example, suppose I were to send that 1 unit between this half in this manner and half in this manner, and similarly for this, half along here and half along here, and finally for this then I can send half a unit like that and half a unit like that. Right? So now I can route all demand. Right? So this is a half integral flow, and we could not route an integral flow. Now in this literature, there's something called the cut condition. So what's the cut condition? The cut condition says that if you have to send flow, if you have to route all the demands, then the capacity of any cut in the graph should exceed the demand that is needed, that you want to send across the cut. Right? So for demands to be fractionally routable, capacity of every cut should exceed the demand. This is called the cut condition. It's necessary, clearly, but not sufficient, as the same example will show. So for here, not the same example. I added another demand edge here. Okay, so now there are 4 demand edges. Now here, if I look at this cut, does it meet the cut condition? The capacity is 3 and the demand is only 1. So capacity exceeds demand. If I look at this cut, once again, the capacity is 3 and the demand is also 3. So it does meet the cut condition, right? The demand is 3 because this demand is separated, this demand is separated, and so is this demand. Okay? But this demand, which has both its endpoints on the same side of the cut, is not separated. Right? Same for this cut, same for this cut, same for any cut in this graph. However, you cannot send this flow in this, right? So the cut condition is met, but this flow cannot, or this demands cannot be routed in this graph. This is a very classic example. It's in fact the smallest example where the cut condition is necessary and not sufficient. And why? What's a simple reason? If any of the students can tell me, why can I not send these 4 units of flow in this graph? Only students? So the cut condition is met, right? But can you see a reason why the flow could not be routed? Okay, let me give you a simple argument. Well, for every demand, the 2 endpoints are separated by 2 edges at least. I need a path of length 2 to route any demand, right? So there are 4 units of demand. I should have 8 units of capacity. But there's only 6 units of capacity in this network. Yes? And so clearly there is no way of routing all the 4 units of demand, even though the cut condition is met. In fact, this is exactly the idea which can be translated by writing a suitable linear program, and you can formulate a necessary and sufficient condition for fractional routing of flows, but not through the cut condition, but through linear programming drive. So this has been studied for a long time. Sanjeev showed an impressive list of papers. I did not put that same list of papers, but it would be equally long. So this is all work that was started in the early 80s, right? A lot of people looked at, especially in the combinatorial optimization community. And so the cut condition is not sufficient for routing of flow. But if in a graph, the capacity of every cut exceeds the demand across the cut by a factor of log n, then the flow can be routed. Right? Not integral, fractional. Right? Integral flow is much harder, so then fractional flow can be routed. And there's an interesting connection of this to the L1 embedding of metrics with minimum distortion. I will not be going into that today. And the connection actually allowed London Lineal and Rabinovich to use a result of Bourgain to obtain that log n result. And that log n that is there is actually tight, which basically means that there are graphs for which you need that the capacity of cuts exceed demand across them by a factor log n to make the flow routable. And these are usually expanded graphs. Now, this is the first open problem. Actually, this is conjectured by Anupam to be a constant for planar graphs. Okay, what is conjectured to be a constant? That in a planar graph, if the capacity of every cut exceeds the demand across that cut by a suitable constant, then flow is always routable. This conjecture has stood for 30 years now, maybe 20 years, whatever, but is still.
Joint graph is planar, or they are separately?
Separately. No, not separately. The graph in which you want to do the routing of flow. What we call the supply graph. If it is planar.
The demand graph as such.
The demand graph would be anything. Yeah. Good question, because the joint graph planar is exactly what this talk is about, right? So so if the planar, the supply graph is planar, and you have some pairs that you want to route, then it's conjectured that you can get a constant approximation. I should also make a pitch for Nikhil, who did in a recent work made good progress towards this conjecture by showing that if the demands are only on some faces of the planar graph, right? So if I take a face of the planar graph and I put the demand edge on that face, and if I have just some such thing, then this conjecture is true. Right? So good. Now, when is this cut condition sufficient that I just talked about? Right? So it's sufficient for 2 classes of planar graphs, which are sort of standard in this community. Lots of people have looked at them. As I said, these are from the early 80s. One is called the Okamura-Seymour setting. Here, you have a planar graph and all the demand is on one face. So when I say demand is on one face, I mean both the endpoints of a demand edge are on the same face of a planar graph. You can assume this is the infinite face, or you can assume, because you can always turn the embedding anywhere around, you can assume it is some face. I have not drawn the rest of the graph. There is a lot of the remaining graph here, which is planar. Right? So the cut condition is sufficient for routing flow fractionally if the graph is planar and all the demand sits on one page, on one face, sorry. And in this talk, we are going to be talking about what are called Seymour instances, where the joint graph, G plus H, is planar. If G plus H is planar, then the cut condition is necessary and sufficient. Additionally, if the graph is Eulerian, this joint graph is Eulerian, then you can also route the flow integrally, for both of the settings. So just so that you're all with me, what's a Seymour instance? The supply graph, you're given a supply graph with capacities on the edges, you're given a demand graph with, we'll assume unit demand, and G plus H is planar. Okay, now I'm going to introduce a new notion, which is what's called a multi-cut. Right? So multi-flow and multi-cut are, so I'm going to also talk about multi-commodity flow. So what's a flow? It's the same thing I said earlier. You want to route flow between, for each demand edge, such that capacities are respected, and a half integral flow is one in which all flow is in units of half, and an integral flow is one in which all flow is in units of one. So in this simple example here, okay, no, so small difference. I want to, in a maximum multi-commodity flow, I want to, okay, so slight difference that I should bring in, I think the slide is missing that. Yes, it is. So I want to maximize the total flow I'm sending, right? The objective is not just to route every demand. I now want to maximize the total flow I'm sending. So here, as this example shows, for this demand, I decided to send 1 unit of flow like that. For this demand, I'm sending 2 units of flow, one in this manner and one in this manner. And for this demand, I'm sending 0 units of flow. I could potentially also have sent 1 unit of flow like that and only 1 unit of flow like this. But what you can see by staring at it long enough is that the maximum flow I can route here is 3 units, not anything more than that. So now in the multi-flow setting, what I'm going to call multi-commodity flow or multi-flow, I want to maximize the total amount of flow. Okay, what's the maximum half integral flow in the same graph? Again, it will turn out to be 3, you'll trust me on that. So this could be a potential routing. Here I routed half a unit, here I routed another half. So these green arcs show the half units of flow that I've routed. What's a multi-cut now? So think of multi-flow as your extension of the idea of a maximum flow, right? So you all learned maximum flow. So there is a source, there is a single sink, and you want to maximize the amount of flow that you're sending from the source to the sink. Now, multi-commodity flow or maximum multi-commodity flow is just an extension of that, except that now instead of one source sink, you have multiple source sinks, and you are trying to maximize the total amount of flow that you're sending over all of these put together. Now, in the case of single commodity, you have a cut, right? What's a cut? A cut is a set of edges which separates the source and the sink, right? What's a multi-cut? It should be a set of edges which separates every source and the sink, right? And so that's exactly what it is. It's a set of edges whose removal will disconnect every sourcing pair or every demand. So here, these dashed edges are 4 edges whose removal will separate every demand pair. So once I remove these 4 edges, I should not have a path left between this vertex and this vertex. You might be tempted to think I can go like that, but remember, it's in the supply graph. So this edge I cannot be using, right? Because then I cannot route here. So I cannot go anywhere further here, and here too I could potentially go all of the way here, reach all of these vertices, but then I will be stuck here, right? So these 4 edges here form a multi-cut. So in this example, the multi-cut is of size 4. And the question I'm interested in is, for these Seymour instances where G plus H is jointly planar, what's the relation between the maximum multi-commodity flow and the minimum multi-cut. Okay, so I'm going to show a tight relation between maximum half integral flow and minimum multi-cut, right? I've not said what the relation is. I've just said it will be a tight relation, which means that I'll also show you an example where that condition is met. I'll also show you that, I'll not show the hardness, but I'll show a 4 approximation for maximum integral flow. We do not know the complexity of maximum half integral flow, but I'll show you a 2 approximation for that, and that will follow from the first result. The minimum multi-cut is NP hard in this setting, but our equivalence to what we'll call the 2H capacity augmentation problem, sorry, 2H connected augmentation problem will imply a polynomial time approximation scheme for a minimum multi-cut. And this will sound very strange because I have not come to this point yet, but there's something called the uncrossable cut cover problem, and I'll show you half integral duals for that. So looks very intimidating. It's not, right? So just work with me, and if you have any questions, stop and ask. Okay, I should point out that, as I said, there's lots and lots of work also in the setting of planar graphs. When I say planar graphs, I mean G is planar and H can be arbitrary, right? That's what I mean when I say planar graphs. So Chekuri, Khanna, Shepard, I think this is the best result known. So they considered edge disjoint paths in planar graphs, right? So which is like maximum integral flow, if you think of it, right? So by edge disjoint paths, so if all the capacities are 1, then an integral flow or maximum integral flow would correspond to edge disjoint paths, maximum edge disjoint paths. And they give 4 approximation for that, but they require that the congestion be 2, right? What is congestion? Congestion means that through an edge, up to 2 paths could use that edge, okay? And this is necessary. If you don't allow congestion, then there is a very old result which shows a root n gap between the maximum fractional flow and the maximum integral flow, which means that the integral flow in that example is just a 1, and the maximum fractional flow can be as large as root n, right? So there is really no hope of getting anything good. And KRR free graphs, in KRR free graphs, this is a recent result where, so this is for multi-cuts now, yeah. So this is for edge disjoint paths, and this is for multi-cut. So multi-cut, the best current known result is a log R approximation. Anupam, I first put your result, and then Nikhil told me कि नहीं अब log R हो गया. Sorry, you. So prior to that, Anupam had the best known result, which was an R approximation for multi-cut, and for a fixed number of terminals, there is a polynomial time approximation scheme. So this is all for planar graphs, and there are many more results. I just put the best results, right? I think even this, prior to that, there was a log n approximation known, and there were other results. So this is a very active area of research, or has been an active area of research. Continues. This is a result from 25. Okay, so very messy, right? Let's. What am I showing here? What I'm showing here is something everyone should know, right? It's just the graph and its planar dual, right? The graph is in bold, the dual is in the dashed lines. The red edges, remember, are the demand edges, and what was black earlier is now blue for some reason, and that's the supply edges, right? So supply demand of the original graph and of the planar dual, right? Okay, so I've just drawn the dual graph.
How do you color the face vertices? Like, how do you assign color to the face?
Have I assigned a color to the face vertices?
Yeah.
No.
They're just all red.
They are just, no, the endpoints of the demand edges, I just made them red. Okay. No, so ignore the color on the vertices, they are not relevant. Yeah? Yeah.
Are the red vertices the dual vertices?
Yeah, the red vertices correspond to the dual. Oh, are all the red vertices dual? Maybe you are right. Maybe that's what I did. Ah, yeah, good, thanks. Yeah. So the black vertices are from the primal graph, and the red vertices are from the dual graph. Okay, Yeah, one thing that I missed out, these two red vertices are identified. They are the same vertex, right? This is the infinite face. So I just could not draw the mesh, so I just split it out. Okay, now, okay, the primal, the multi-cut edges, right? So remember we had, what did we have? We had corresponding dual edges. So this was a multi-cut, right? That I had shown you. It's the same running example that I'm continuing with. And I'm taking their, so these are in bold, and their duals are correspondingly also in bold. Okay. Now I'm going to throw away the primal graph, and this is what I'm left with. Okay, and now this is the important connection that we want to make. So these are the demand edges, and these are the multi-cut edges. And what are the multi-cut edges? The multi-cut edges are chosen in such a manner so that every demand edge is on a cycle. Okay. So the multi-cut in the planar dual is a set of edges such that every demand edge is part of a cycle. Every demand edge in the dual graph. Right, and you can convince yourself about that, hopefully. Yeah, let's see why. So this demand edge is going to be on this cycle, which is that. Going back here, going here, going here, and going there. So every demand edge will be on a cycle. So now, then so this is an observation. And so a minimum multi-cut is now same as finding. So we go to the dual and we say, okay, find a minimum cost set of supply edges now, such that every demand edge is sitting on a cycle. And we'll call this the two-edge connectivity augmentation. Right? So two-edge connectivity, usually augmentation would mean that you want to make the entire thing two-edge connected. Here we just want sort of two-edge connectivity on the demand edges. So you just want every demand edge to go into a cycle. But we'll just use this term. Okay? So let me define the problem once again for you. You're given a graph, V. There are two kinds of edges, blue and red edges. You want a subset of the blue edges of minimum cost such that every red edge, which is in F, sits on a cycle. Okay? And now I'm going to put another formulation to this, which is now I'm going to, this is where my training on proper functions and given Williamson comes into play. So I'm going to now define a function which has on sets of vertices, and so the definition is here. So if a set of vertices here has only one red edge across it, okay, then what do I want? I want one blue edge to go across it too, right? Because that's, you know, that if I have to pick a set of blue edges so that they form a cycle for every red edge, then I need any set which has only one red edge across it should also have, I need to pick one edge across that set also. So that's exactly what is said here. So I'm going to define this function on sets of vertices. I'm going to give a set S a requirement. F of F is called the requirement function. I'm going to give it a requirement of a 1 if there is exactly one red edge. So delta S intersection F, F is a set of red edges, is exactly 1. Okay? So set S has a requirement 1 if and only if it has exactly one edge of F across it. And now, again, reformulating this, you want to find a minimum cost E prime such that delta S intersection E prime is greater than or equal to F of S, right? Such for every set S, I want to meet the requirement, right? If the requirement is 1, then E prime should have an edge across that set. If the requirement is 0, I don't really care. Yes?
This function is 0 otherwise.
Sorry?
The function F?
Yeah, this function is a 0, 1 function.
Okay.
Yes? So it's 1 defined only for sets of vertices such that there is only one red edge across it. Okay, now this function is what's called an uncrossable function, right? So what's an uncrossable function? So the definition is up here. This is a picture representing that. If the function is 1 on these two sets A and B, then either it is 1 on the union and the intersection, or it is 1 on the symmetric difference. Then it's called an uncrossable function, right? And without proof, I'm going to just make the claim that this function that we defined earlier is an uncrossable function. Is it getting too technical?
No.
I'm throwing too many terms at you, right? Yeah.
No.
No? Okay, more coming. Okay, so what do we do now? So now this becomes this kind of, sort of it's bringing into the framework of, the kind of work that was done for network design for many, many years. You have a requirement function, you want to pick a set of edges such that all those requirements are met, and you will formulate a linear program for that, which is exactly this. You want to xc is 1 if I pick that edge, it's 0 otherwise, that's an integer version. You want to minimize the cost of the edges. For every set of vertices, you want to pick xc such that for every set of vertices, the requirement, the number of edges across the set is at least the requirement. And then that's the standard linear programming dual. Right? Now this is LP dual. Earlier I was talking of planar dual. So there are two duals in this talk. And this was an old algorithm from the 90s. Williamson, Giemans, Mihail and Vazirani, which worked for such functions. Gave a two approximation. So it's a primal dual algorithm which computes a dual solution. What's a dual solution? Okay, let me tell you what the dual solution here is. The dual solution is an assignment of values to sets of vertices. So ys is a value that I assign to a set of vertex, and it's a packing of these, right? So you want to assign these values to set, such that if I take any edge and the total value assigned to the sets for which this edge is going across, that should be less than the capacity of the edge, and it's a non-negative assignment of values, right? And you want to pack as many sets as possible. And which sets are you interested in? Only the ones which have a requirement of a 1. Okay? So, right. So basically they showed a two approximation algorithms. However, in this algorithm, these dual variables need not be half integral. Okay? Now this is a cryptic line here. Why should we care about these dual variables being half integral? Right? So this WGMV algorithm will compute a set E prime, right? So this is, when it computes a set E prime, it means an integral solution to the primal program. But the dual solution is, could be anything. Now, what I'll show you in the later part of this talk is, how much time do you have? 10 minutes? 15 minutes. You're being generous. So, I go back. So what I'm going to show you is that that these dual variables that I'm raising here are actually going to correspond to flows in the Lie graph. So I want these dual variables to be half integral so that my flows there are half integral. Right? That's the connection. I should perhaps have moved that slide earlier, but take it. Right? So the Williamson et al. Algorithm is quite straightforward. And many of you would perhaps have seen something like this in an approximation algorithms course if you've done that, or if you've taught it. So what you do is you call a set unsatisfied if its requirement is 1, but there is no edge across it yet. You look at all your collection of unsatisfied sets. You find the minimal unsatisfied sets. You take all these minimal unsatisfied sets and you start increasing their dual variables till some edge goes tight. An edge goes tight when the total dual variables equal to its capacity, and you add these tight edges to your set F. F is the set of edges that you are picking up. Right? And you keep doing this, and there's also a reverse delete phase where you just throw away the edges which are not needed. Right? So fairly standard stuff. Now what happens? Let's look at this example. Right? So these are the red edges. So this is the 2-edge connectivity augmentation problem. These are the red edges. I have to pick the black edges in such a manner such that every red edge is on a cycle. Right? So which basically means I have to pick both these black edges. So optimum solution is completely clear. Let's see what the WGMV algorithm is going to do here. Right? So this set and this set and this set are going to be your initial minimal unsatisfied sets. You can see that they are singletons, so minimal does make sense, and they are all unsatisfied because I have not yet picked this edge, right? So there is only one red edge going across that. This is not an unsatisfied set because there are more than one. This doesn't have a requirement of a 1, right? Only these 3 edges have. So you raise their dual, and remember these edges have capacity 1, so both of these increase to a half, and then this edge goes tight. So at time equals half, this goes tight, and this is also at a half. And now what's going to happen, right? This whole thing becomes a minimal unsatisfied set. Yeah, why? Because this is satisfied now, these two. This doesn't have a requirement of a 1. This becomes minimal unsatisfied. So you're going to increase its dual value. This is already at a half. You're going to start increasing this. So you'll increase it to a quarter, and this will also increase to a quarter. Right? So this will finally be half, a quarter, a half, and a half. This is not a half integral solution. Yeah? So the WGMV duals actually fail, and they do. WGMV is actually an extension of the Giemans-Williamson algorithm, and the Giemans-Williamson algorithm worked for a setting of what was called the proper functions, and for proper functions. So what is a proper function? A function is proper if a set is 1, then no matter how I break that set up, right, one of the sides is at least a 1. So the proper function, proper functions are, if a function is proper, it's also an uncrossable function. And for proper functions, the Giemans-Williamson algorithm works for proper functions, and it actually gives half integral duals. And actually I have, so now here is an, okay, so should I go through this? Okay, maybe I should, I'll make an attempt, right? Let's see how many of you were able to follow. So this is actually the idea that we use, right? So maybe I should say a little words about this slide. So what's the idea we use? So in the proper, when we are looking at the proper functions, we said, how does one argue half integrality of these, right? And we said, okay, let's look at a vertex, and let's define the parity of a vertex, right? So let's take a vertex, let's say I constructed the entire dual equation, and let me look at all the sets that this vertex was sitting in. Was there a question? No, okay. So let me look at all the sets this vertex was sitting in, and let me sum up the dual values of all of those sets. And now let me take the fractional part of it, right? I'm going to call that pi of v, the parity of the vertex v. And that's the very first line that I've defined. The claim is all vertices in a set for which I have okay, all vertices in which set, this should perhaps be a set for which I have raised the dual value, right, which was ever active. They will all have the same parity. Yeah.
Are you arguing that every step of the algorithm or the final solution? Like you're arguing that's what the GWS algorithm.
I'm talking about the GW algorithm.
And every step of the algorithm you're arguing this.
Yes.
Okay.
Yeah. So if I have an active set A at any step of the algorithm, then there will always be a vertex inside the set which was always active, which was always sitting inside active sets, right? Because the way the Giemans-Williamson algorithm works is you are starting some vertices, you are increasing their duals, maybe they combine with some other sets. This whole set either becomes inactive, fine, or maybe it remains active and then the whole thing increases and so on and on. So the point, if you think about it and if you remember the algorithm, is that if there is an active set, there is always some vertex inside the set which has always been inside active sets. Okay, so they will always contain a vertex which has always been inside active sets, and therefore the parity of this vertex is the same as the parity of the current time t. What do I mean by parity of the current time t? If t is 3.5, then the parity of this vertex is half. If t is 3.3, the parity of this vertex is 0.3. Right? Because it has always been part of an active set. Right? So fractional part. Now when two active sets combine along an edge, what happens? Right? all vertices on this set have the same parity, all vertices in this set have the same parity, right? Now look at this edge, which is integral, right? It's getting tight. What does that mean? That means that its two endpoints should have, when it becomes tight, should have a parity of half, right? That's because they have the same parity, right? Which is the current time, right? When this thing got merged. So when two active sets combine along an edge uv, then phi of u is phi of v, which is the current time. And since this edge is integral, this parity of the current time is also a half, is either a 0 or a half. And all vertices in the combined set will therefore again have the same parity.
Where do you use properness?
Where did I use properness in this argument? No, I did not use properness in this argument.
Then something has to fail for the previous.
Okay.
There's always a vertex inactive.
Sorry, come again? Okay, yeah, okay, good
Maybe
point.
the one about there's always a vertex which has always been
The same parity as okay, so let's go back to the previous example. Good point. Let's go back to this example. Here, this vertex, right? So these had the parity half, and this did not have parity half in this set. Right? This had a parity 0 because this was never part of an active set. Right? So that's where that fails. Okay. And so this is the idea, this is the key idea. Now let me skip a few slides here because, okay, so what is it that we did? So we used this idea, we went into WGMV, we had to strengthen the analysis, we sort of redid the analysis of WGMV, and these are slides for that. I do not know why I made this, but it's okay, maybe some other talk, right? And so the end result was that we could modify the algorithm, and the modification is actually fairly easy, right? So we modify the, so we sort of reduce, so if some edge is threatening to be, make it look bad for us, then we'll just reduce the cost of that edge, right? So we'll pretend that it has actually cost less than what it actually has, right? So which basically means that we have to strengthen the analysis to argue that, so here, just so that I can quickly get to what I'm trying to say, instead of 1, I'm going to pretend that this edge has cost of a half, okay? And then everything would work fine, right? Because this would be at a half, this would be at a half, this would be at a half, and then everything would just disappear. Right? So we'll pretend that it has a, so this is what I meant by reducing the cost of the edges. Of course, the analysis has to be strengthened, right? In this example, it's trivial, so half and half and half is 3 halves, and I'm only, a cost is a 2, right? So it's within the factor 2 that I want it to be. But this can always be done, and that basically requires me to sort of do some grunge work and make sure that the WGMV analysis can support this. So we did that. Let me show you, come to the part. So this then becomes our main theorem, which is saying that, so this is nothing to do with planar graphs, by the way. This is, no, just graphs, right? So for uncrossable functions, we can compute a set of edges and a half integral dual, so that this holds true, right? So this then this is from the ESA paper that I mentioned. And now how does this connect to the first part of the talk, which is about Seymour instances? So I increase the dual of a set only when its requirement is 1. Now remember, which sets did I keep with requirement 1? These were one which had only one red edge going across them in the dual graph. So what does that mean in the planar graph? That means that they correspond to a face of the planar graph or some other region of the planar graph, but that has only one red edge across it. So which means that the rest of the edges are blue edges. So which means when I increase the dual, I can think of it as if I'm increasing the flow along this path. Right? So show you a picture, right? So when I increase this dual here, which, right? So this is a vertex in the dual, planar dual. This is a set whose dual I increased. When I increase this dual, remember I increase this dual because there is only one red edge across it. In the planar graph, planar primal, there is only one demand edge. Increasing this dual it corresponds to sort of sending this unit of flow. Okay? And that we can do, so even here for instance, these two sets may be combined, I increase the dual of this. There is only one, because this has a requirement of one, there is only one red edge going across it, which means that this is sort of, this is not a face of the planar graph. This is a region of the planar graph along which I can now send flow.
This is where you're using planarity.
This is where we use the planarity. To connect the half integral duals that we built, the half integral duals have nothing to do with planarity, but we sort of did all of that work so that we could do something like this. Okay, it's good. So the fact that the duals form a packing means that, okay, so this is a capital sigma, this is sum and not the little sigma. Okay, so sum of Ys is less than capacity, and so the total flow will be here. Okay, so I think I'm almost out of time, I hope I am, because this is pretty much my last slide. So, so this gives us this theorem, right, that the minimum multi-cut, which basically is coming from the extension, the WGMV thing that I showed you. So minimum multi-cut is, this is straightforward. This is the part we've shown, is less than 2 times max half integral flow. This 2 is coming from the WLGV result. And it's a half integral flow because the duals that we had was half integral. Okay, now this is an example that we stole from Joseph Chelian, right? From the tree augmentation problem. I think they had some nice examples. So surprisingly, it also gave us a bad example, right, for our problem. So, so this example here has a minimum to multi-cut of size k minus 1. Okay, so what is this example? The blue again are the supply, these are the demands. And there is of course these demands, but there is also demand from this vertex to this vertex. So essentially 2 vertices removed, right, down this ladder. So every demand, the endpoints of every demand are removed by a path of length 3, right? In this case here, and in this case here, symmetric, right? So by the argument I showed you initially, the maximum flow you can route is how much, right? So total capacity, if there are k such blocks, the total capacity is 2k, and each path uses 3 edges. So maximum flow you can route is 2k by 3. That's fractional flow. Maximum half integral flow, and this requires a little bit of proof, so I'm not going to show it to you, is k by 2. The minimum multi-cut is k minus 1. And so that actually shows that this relation that we put up here is tight. Okay, we can convert this half integer flow into an integer flow as well, right? But we have to lose another half in the process. And this this is not completely standard. I think this also required some interesting ideas, and one of which was to use a 4-color theorem. So this then gives us, so the same result if you want to formulate it in terms of integral flow, this is what you'll get. The multi-cut is at least the maximum integral flow, but at most 4 times the maximum, oh sorry, cut and paste error. This should be integral flow. But the previous example only shows a gap of 2. So in the previous example, the maximum integral flow was also k by 2. And that should be easy to see. I can always take alternate pairs and route integral. So you can get a k by 2 very easily, but that's also max. And so that's where some gap is. You know, if you are interested, you could try to get a 2 approximation for maximum integral flow. And I said that's a hard problem, NP hard. The maximum half integral flow, we do not know whether it's NP hard. So it could potentially have a longer time argument. Okay, yeah, thank you.
Do we have any questions for Professor Louis? Are there implications for like L1 embeddings for planar graphs, like the Bourgain style connections?
Yeah, this should all translate into that.
Okay.
But this would not be for